Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are going to settle into a question that sounds simple at first, almost like something from a school lesson. But the longer you sit with it, the stranger it becomes. How many states of matter actually exist? Most of us grew up hearing the familiar answer: solid, liquid, and gas. Perhaps later someone added plasma, usually with a quick mention of lightning or the sun, and then the lesson moved on as if matter had politely finished introducing itself. But matter, as it turns out, is not quite so tidy. It has more moods than a rainy afternoon, more disguises than a stage actor with a very patient wardrobe assistant, and far more ways of behaving than the old three-part list suggests. Before we begin, I would love to know where you're listening from tonight. Are you somewhere quiet and dark with the day already folded away? Or is it still bright outside where you are, with matter in all its forms moving noisily around you, cups being lifted, doors being closed, water boiling, air shifting, screens glowing? It is always a gentle thought, this little community scattered across the world, each person surrounded by the same universe, but meeting it through a different room, a different window, a different hour. And if you find this slow journey soothing, or if it helps you settle down while still keeping a small candle of curiosity lit in the mind, I would be very grateful if you gave the video a like and subscribed. It helps this quiet corner of science reach other people who may also want to drift off with something thoughtful, calm, and just strange enough to keep the imagination warm. Now, as we begin, try looking around the room you are in. You do not need to move. You do not even need to open your eyes if they are already feeling heavy. Just imagine the things near you. A blanket, perhaps. A pillow. A glass of water on a bedside table. The phone or screen that is playing this voice. The air moving in and out of your lungs. Maybe a lamp, a book, a wall, a window, a warm drink, or a cold one. It all seems so ordinary because your brain has spent a lifetime sorting it into simple categories. The bed is solid, the water is liquid, the air is gas, the light from the screen is something else, but we usually do not think too much about that unless we are trying to sleep, and the screen is being a little too enthusiastic about existing. Matter is the stuff that makes up the things we touch, hold, breathe, eat, spill, clean, break, repair, and occasionally lose under the sofa. It is in the chair beneath you, the dust floating in a sunbeam, the steam rising from a kettle, the ice cube shrinking in a drink, the metal spoon resting on a table, and the tiny living cells quietly working inside your body. When we first learn about matter, it feels sensible to describe it by shape and movement. A solid keeps its shape, a liquid flows, a gas spreads out. That is useful. It is clear. It is the kind of explanation that fits nicely on a classroom poster. But the universe has never been especially committed to fitting on posters. The first clue that matter has deeper possibilities comes from change. Ice does not always stay ice. Warm it gently and it becomes water. Warm that water more and it becomes steam. Cool the steam and it becomes water again. Cool the water and it becomes ice. It feels like a simple costume change. Same substance, different behaviour. But beneath that familiar transformation, something remarkable is happening. The tiny particles inside the matter are not changing into different particles. They are arranging themselves differently. They are moving differently. They are holding on more tightly or letting go more freely. Matter is not defined only by what it is made of. It is also defined by how its parts are organised and how those parts are allowed to move. That is where the idea of states of matter becomes more interesting. A state of matter is not just a label. It is a way that matter behaves under certain conditions. Change the temperature, change the pressure, change the magnetic environment, change the density, or push matter to an extreme place like the centre of a star or a laboratory, colder than deep space. and matter can begin to act in ways that ordinary kitchen examples never prepared us for. It can flow without friction. It can conduct electricity in strange ways. It can become so spread out that its particles move almost freely, or so compressed that normal atomic structure begins to collapse. It can behave like many separate things, or, under very cold conditions, almost like one single shared thing. Matter is not a fixed set of boxes. It is more like a landscape, with familiar towns near the road and strange hidden valleys far beyond the map. For most of daily life, the old three states work perfectly well. You can make breakfast, take a shower, walk in the rain, build a house, boil pasta, and complain about humidity without ever needing to mention anything beyond solids, liquids, and gases. A table does not suddenly become a superfluid halfway through dinner, which is probably for the best. A cup of tea does not turn into quark matter while you're deciding whether it's still too hot to drink. The world we live in is comfortably ordinary, because our temperatures and pressures are fairly ordinary. Earth is a gentle middle ground where many materials stay in familiar forms, at least most of the time. This can make the universe seem simpler than it is. But Earth also gives us hints. Fire does not behave like a solid, liquid, or gas in the usual sense. Lightning tears through the sky in a bright flash of charged particles. The sun, which looks so steady and simple from far away, is not made of normal flame at all. It is a vast glowing ocean of plasma, a state of matter so common in the universe that our everyday solids and liquids are actually the local oddities. The stars are not unusual because they are plasma. We are unusual because we spend our lives touching wooden tables and drinking liquid water and thinking those are the main forms matter prefers. That is one of the quiet surprises of this subject. The matter around us feels normal because it is close, not because it is the most common. Most visible matter in the universe is in plasma form, inside stars or spread through space in hot charged clouds. If a distant alien physicist were making a very sleepy science video somewhere near a cluster of stars, they might begin not with solids, liquids and gases, but with plasma, and then mention solids as a rather curious chilled condition found on small rocky planets. It is always humbling when the universe reminds us that our everyday experience, useful as it is not the whole story. It is just the part of the story that happens to fit under our feet. The question of how many states of matter exist depends partly on what we mean by count. If we only count the broad, familiar categories, we get a short answer: solid, liquid, gas, plasma. Add a few more famous ones, and the list expands. Bose-Einstein condensates, superfluids, superconductors, supersolids, degenerate matter, quark-gluon plasma. Look deeper into modern physics, and the borders become less like neat fences and more like soft fog. Some states are phases of matter, some are special conditions of known phases, some happen only under extreme cold, extreme heat, extreme pressure, or inside astrophysical objects we cannot visit. Some are well confirmed in laboratories, some are theoretical, some are so specialized that they do not show up in ordinary conversation unless the conversation has already taken a very unexpected turn. So when someone asks how many states of matter actually exist, the most honest answer is not a single number. It is a journey. It depends on how carefully you look, how strict your definitions are, and whether you are speaking like a school textbook, a chemist, a condensed matter physicist, or a person who has simply noticed that custard behaves suspiciously when you hit it with a spoon. Even in the everyday world, matter does not always behave as cleanly as our categories suggest. Some materials are gels, some are foams, some are glassy solids, where the particles are arranged in a disordered way that feels almost liquid, like at the microscopic level, even though the object sits there looking solid enough. Some fluids thicken when stressed. Some flow slowly over long times. Some are soft, some granular, some elastic, some sticky, and some seem to have attended a private meeting where they agreed not to behave properly in front of humans. Think of honey, slowly folding over itself as it pours. Think of sand, which can sit like a pile, flow like a liquid, or jam like a solid depending on what you do to it. Think of toothpaste, which holds its shape until squeezed, then suddenly decides it can travel. Think of whipped cream, fog, smoke, jelly, mud, glass, rubber, snow, and foam. These things remind us that the everyday labels are helpful, but not complete. Matter is not always polite enough to choose one simple identity. Sometimes it lives near the border, and the border is often where the interesting things happen. Physics likes categories, but nature likes behaviour. That is why states of matter are best understood not as names to memorize, but as patterns to notice. How tightly do the particles hold together? How freely can they move? Do they keep a fixed arrangement, or do they slide past one another? Are they electrically neutral, or have their electrons been stripped away? Are they acting as individuals, or are they entering a shared quantum condition where the usual separateness begins to blur? These questions lead us gently from the world of ice and steam to the glowing interiors of stars, the coldest laboratories on Earth, and the crushed hearts of dead suns. There is something comforting about this if you let it be comforting. The universe does not become stranger because our first lessons were wrong. They were not wrong. They were starting points. They were the front door. Solids, liquids, and gases are real and useful. They are how we begin to understand the material world. But science often works by taking a simple idea and asking what happens when the conditions change. What happens if matter becomes much hotter? What happens if it becomes much colder? What happens if it is compressed beyond ordinary limits? What happens if the particles no longer behave like tiny separate beads, but like a shared quantum crowd? The answers do not erase the simple picture, they deepen it. And this is a lovely kind of question for a sleepy evening because it lets us move slowly from the familiar to the astonishing. We do not need to leap straight into the most exotic corners. We can begin with the things we already know. A solid piece of ice, a liquid glass of water, a breath of gas in the lungs. From there we can warm the picture, loosen the bonds, let particles move more freely, and eventually watch ordinary matter become plasma, the bright charged state that fills the stars. Then we can cool matter down beyond anything nature usually provides on Earth, until atoms begin to lose their separate identities in a strange collective stillness. We can look at materials that flow without ordinary resistance, matter that conducts without losing energy, matter inside white dwarfs and neutron stars, and matter that may have filled the universe when it was extremely young and unimaginably hot. But for now, before we travel outward to stars or inward to particles, it is enough to sit with the simple strangeness of the room around you. Everything nearby is matter arranged into behaviour. The blanket is not just a blanket. It is countless atoms held in a structure that gives it softness and shape. The water in a glass is not simply wet. It is a moving collection of molecules that cling, slide, ripple, evaporate, freeze, and return. The air is invisible but not empty. It presses gently against your skin, carries sound to your ears, and moves with each breath. Even the warmth you feel is part of the story, because temperature is connected to motion, and motion is one of the quiet ways matter tells us what state it is in. If your eyes are closed now, you can imagine the world not as objects but as arrangements. The wall is matter locked into structure. The air is matter wandering freely. A warm drink is matter flowing in a cup while a thin trail of vapour escapes above it. Somewhere beyond the ceiling, clouds are gathering or dispersing. Somewhere beyond the clouds, the upper atmosphere is full of charged particles and faint invisible activity. Far beyond that, the sun is shining as plasma. Far beyond that, old stars are collapsing. Cold clouds are drifting, and laboratories on Earth are coaxing atoms into states so delicate they can only exist under careful protection from the noisy warmth of ordinary life. This is the real invitation of the question. How many states of matter actually exist? It asks us to look again at the things we thought we knew. It asks us to notice that a simple ice cube is part of the same grand subject as a star, a superfluid, a neutron star, and the earliest moments of the cosmos. It asks us to see matter not as still stuff, but as a set of possibilities. Matter can be rigid or flowing, invisible or glowing, ordinary or extreme, calm or violently energetic, spread across space or squeezed into densities that make imagination quietly step back and ask for a chair. So settle in now, gently and without hurry. Let the old classroom list return for a moment, not as the full answer, but as the first step. Solid, liquid, gas. 3 familiar words for the familiar world. They are the doorway into everything that follows. They are the states we meet with our hands, our breath, our kitchens, our weather, and our sleep. And as we move from the things that hold their shape, to the things that pour, to the things that drift unseen through the room, we begin to see why the story of matter could never remain as simple as 3 neat boxes on a page. The world begins for us in solids. Long before we learn the names of atoms or molecules, before anyone tells us about pressure or temperature or microscopic motion, we meet matter first as something that can be held. A crib, a spoon, a wooden floor, a stone in the hand, a blanket tucked under the chin. These things seem dependable. They stay where we put them, more or less. They do not spread across the room like a smell, or pour off the table like water, unless something has gone very wrong with the furniture. A solid is the state of matter that feels most like the world has made a promise. It has shape. It has edges. It resists us gently or firmly when we press against it. It says, in its quiet material way, I am here. Of course, that feeling of stillness is a little deceptive. A solid looks calm because its inner motion is hidden from us. The atoms inside it are not frozen into absolute silence. They are vibrating, shifting slightly, nudging one another in tiny restless ways. Even a cold stone is not truly still. It only seems still because its particles are locked into a pattern and cannot wander freely through the material. They're rather like people standing in a very crowded theatre lobby, able to wiggle, turn and grumble quietly, but not able to drift across the building without everyone else getting involved. That arrangement gives a solid its shape. The particles are held close together by forces that keep them in place, and because of that, the object can sit on a table, form a bridge, become a mountain, or be used as the very important object known as a biscuit tin. This is why a solid can be carved, stacked, polished, broken, bent, or built into something larger. The particles inside are arranged in a way that makes the material hold together. But not all solids are the same kind of solid. Some are crystalline, meaning their particles are arranged in orderly repeating patterns. Salt, diamonds, many metals, and ordinary ice have this kind of internal order. If you could shrink down and walk through a crystal, which would be a rather hazardous holiday, you would see a repeating structure stretching around you, a microscopic architecture of remarkable regularity. That hidden order gives many crystals their clean shapes, sharp angles, and predictable ways of breaking. Other solids are more disordered. Glass is the famous example. It feels solid. It holds its shape. It can shatter your favourite mug with no concern for your emotional attachment to it. But inside, its particles are not arranged in the neat repeating pattern of a crystal. They are locked into a more irregular structure, almost as though a liquid were cooled so quickly that it could not properly arrange itself before becoming rigid. This does not mean glass is secretly flowing down your windows over centuries in the dramatic way people sometimes claim. But it does mean that glass reminds us something important. Even the word solid covers more variety than we first imagine. Solidity is not one single personality. It is a family of behaviours. Some solids are hard, like diamond. Some are soft, like wax. Some are elastic, like rubber. Some are brittle, like dry clay. Some can be bent into wires, beaten into sheets, stretched, moulded, or snapped. Metals shine and conduct heat because their electrons are able to move in special ways through the material. Wood is full of fibres and old living structure. Bone is strong but also slightly flexible, which is useful because a skeleton made of something as brittle as dry toast would make daily life more complicated than it already is. A snowflake is a solid, a steel beam is a solid, a grain of sand is a solid, and the crust of the earth beneath a sleeping city is solid too, though over very long times even rocks can creep and deform under pressure. Matter, as usual, enjoys making the simple answer more interesting. When enough heat is added to a solid, the hidden vibrations inside it grow stronger. The particles jiggle more energetically, pushing against the forces that hold them in position. At first, the object simply warms. A metal spoon in hot soup becomes uncomfortable to hold. A pavement under summer sun stores heat. A piece of butter left too near a warm window begins to soften, which can feel like a small domestic tragedy if toast is involved. Eventually, for many materials, the particles gain enough motion to break out of their fixed arrangement. The solid loses its rigid structure and becomes a liquid. It does not stop being matter. It does not usually stop being the same substance. It changes how its particles relate to one another. Liquids are the great compromisers of the everyday world. They have volume, but not a fixed shape. They gather, flow, drip, ripple, splash, and settle into whatever container is unfortunate enough to be responsible for them. A liquid is matter that still holds together, but not so tightly that its particles are trapped in place. They remain close, yet they can slide past one another. This is why water in a cup takes the shape of the cup, water in a river takes the shape of the land, and water spilled on a desk takes the shape of a small emergency. A liquid feels more alive than a solid because we can see its motion. It pours from one vessel into another. It forms waves. It swirls around a spoon. It finds low places. It reflects light in trembling patterns. And yet, even when a liquid sits quietly, its particles are moving constantly. They tumble and slide, held near one another but never fully locked. This gives liquids their familiar behavior. They cannot easily be compressed because the particles are already close together, but they do not hold a fixed shape because those particles are free to rearrange. Water is the liquid we know best, not because it is simple, but because our lives are built around it. It fills oceans, falls as rain, runs through rivers, moves through our blood, and waits patiently in kettles for humans to remember they turned them on. Water is so common in our experience that it can make liquid seem ordinary, but water itself is deeply unusual. It expands when it freezes, which is why ice floats. This matters enormously for life on Earth. If ice sank, lakes and oceans would freeze from the bottom upward, changing the story of the planet in ways that would make winter much less picturesque and biology much less convenient. Water also has a high ability to store heat, which helps moderate climate and body temperature. It clings to itself through surface tension, allowing small insects to walk on it and droplets to bead on a leaf. For something we casually spill, drink and bathe in, water is quietly extraordinary. But liquids are not all water-like. Mercury is a metal that is liquid at ordinary room temperatures, shining and rolling in little silver beads, though it is also toxic and should not be treated like a toy, no matter how fascinating it looks in old science footage. Oil flows differently from water. Honey flows more slowly, as though it is thinking very carefully about each step. Lava is molten rock, thick and glowing, moving with terrible patience down a volcano. Liquid nitrogen is so cold that it boils away in ghostly clouds at room temperature. Alcohol evaporates more readily than water. Molten metals can be poured into molds and cooled into solid shapes. A liquid is not defined by being gentle or wet in the everyday sense. It is defined by the way its particles remain close while still being able to move past one another. The way a liquid flows is called its viscosity. A thin liquid like water flows easily. A thick liquid like syrup flows slowly. This difference comes from how strongly the particles interact and how easily they slide. There are liquids that behave politely under normal circumstances and then become stubborn when stressed. Cornstarch mixed with water is a famous kitchen experiment, forming a mixture that can flow slowly but stiffen when struck. It is not a simple liquid in the textbook sense, but it is a helpful reminder that matter often lives in the messy middle between categories. The everyday world is full of materials that do not care much about our neat labels. Mud, cream, paint, toothpaste, melted chocolate and custard all have their own rules, and some of those rules appear to have been written after a long lunch. If heat continues to enter a liquid, the particles move faster and faster. Some escape from the surface as vapour, which is why a puddle can dry even when it is not boiling. Evaporation is a quiet leaving. Molecules at the surface gain enough energy to break away and drift into the air. Boiling is more dramatic. When the whole liquid reaches the right condition, bubbles of vapour form within it and rise upward. The liquid becomes a gas. Again, the substance has not necessarily changed its identity. Water becomes water vapour. It is still made of the same kind of molecules, but now those molecules are much farther apart and moving freely through space. Gases are the invisible wanderers of ordinary matter. A gas does not keep its own shape or volume. It expands to fill whatever container it is in, whether that container is a balloon, a room, a lung, or the lower atmosphere of a planet. The particles in a gas are far apart compared with those in a solid or liquid. They move rapidly, colliding with one another and with the walls around them. This motion creates pressure. You may not see the air in a bicycle tyre, but you can feel its pressure when the tyre becomes firm. You may not see the atmosphere pressing on you right now, but it is there, weighing down gently from every direction, so familiar that your body treats it as normal. We live at the bottom of an ocean of gas and rarely give it the respect an ocean deserves. Air feels like nothing until it moves. A still room seems empty, but a breeze crossing your face suddenly reveals that invisible matter is present. Wind is not emptiness travelling quickly, it is gas in motion. It can turn turbines, carry seeds, shape deserts, lift birds, bend trees, and knock over an umbrella with the confidence of a much larger animal. Sound also depends on gas, at least for us here on Earth. When someone speaks, their voice travels as pressure waves through the air. Without air, there is no ordinary sound to carry the voice. This is why space, despite being full of events, is not full of noise in the way films sometimes suggest. Explosions in vacuum may be visually dramatic, but they are not especially chatty. Gases are easier to compress than liquids or solids because their particles are far apart. Push them closer together and the gas takes up less space, at least until other effects become important. This compressibility is central to engines, weather, breathing, refrigeration, and many technologies that quietly support modern life. When you breathe in, your lungs expand and air flows in because of pressure differences. When you breathe out, air leaves again, carrying carbon dioxide from your body. It is a gentle rhythm of gas exchange, happening without ceremony thousands of times each day. There is something rather intimate about breathing when you think of it this way. The gas outside becomes part of the inner work of the body for a moment, then returns to the world changed. The atmosphere itself is a mixture of gases, mostly nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, water vapour and other components. We often speak of air as though it were one thing, but it is more like a crowd. Each kind of molecule has its own role, its own behaviour, its own importance. Oxygen supports the chemistry that keeps many living things alive. Carbon dioxide, though present in much smaller amounts, plays a major role in trapping heat and regulating climate. Water vapour shapes clouds, humidity, storms, and the comfort level of anyone with hair that responds dramatically to damp weather. The air around us may be invisible, but it is a busy material system. Solids, liquids, and gases are often taught as if they are separate kingdoms, but in real life, they're constantly changing into one another. Water freezes into ice, melts back into liquid, evaporates into vapour, condenses into droplets, and falls again as rain or snow. This cycle shapes landscapes and weather. It carves valleys, feeds rivers, builds glaciers, and paints bathroom mirrors with fog when someone takes a shower that is perhaps a little too enthusiastic. Matter moves between states because temperature and pressure alter the balance between particle motion and particle attraction. Heat tends to loosen structure. Cooling tends to encourage order. Pressure can force particles closer together or change the conditions under which a substance changes state. This is why boiling depends not only on temperature, but also on pressure. Water boils more easily at high altitude because the air pressure is lower. On a mountain, the atmosphere presses down less strongly, so water vapour can form more readily. Deep in the ocean, where pressure is enormous, water can remain liquid at temperatures that would make it boil at the surface. The state of matter is not decided by temperature alone. It is a conversation between energy, pressure, and the nature of the substance itself. Matter is always negotiating with its surroundings, which is relatable in a way. There are also special moments called phase transitions, where matter changes state. Melting, freezing, boiling, condensation, sublimation, and deposition are familiar examples. Sublimation is when a solid changes directly into gas, skipping the liquid state under certain conditions. Dry ice does this, turning from solid carbon dioxide into vapour and producing those theatrical white clouds that make punch bowls look as if they are planning something mysterious. Snow and ice can also sublimate slowly in cold, dry air. Deposition is the reverse, when gas becomes solid directly, as when frost forms on a cold surface. These transitions remind us that the path between states is not always the simple schoolbook route, from solid to liquid to gas. Matter sometimes takes shortcuts. Even the boundaries between these states can blur. At high enough temperature and pressure, the distinction between liquid and gas can vanish. A substance can become a supercritical fluid, a strange condition where it has properties of both. It can flow like a gas while dissolve in materials like a liquid. Supercritical carbon dioxide is used in processes such as decaffeinating coffee, which means that somewhere in the story of your morning cup, there may be a state of matter quietly refusing to be classified. This is not one of the familiar three in the simple sense, but it grows naturally from understanding how liquids and gases relate. The closer we look, the more we see that nature often prefers smooth transitions where our language prefers boxes. Still, the familiar three remain powerful because they explain so much of human experience. Cooking is a daily theatre of phase changes. Butter melts, water boils, steam condenses on a lid, sugar dissolves, bread forms a solid structure as heat transforms its ingredients. Ice cream softens, which is both a physical process and a test of patience. Weather is another grand performance of the same ideas. Clouds form when water vapour condenses into droplets or ice crystals. Rain falls when droplets grow heavy enough. Snow forms when water takes solid shape in cold air. Fog is a suspension of tiny liquid droplets close to the ground. Dew appears as invisible vapour becomes liquid on cool surfaces. The sky is not merely a backdrop, it is a moving lesson in states of matter. The human body is also full of these familiar states. Bones and teeth are solid structures. Blood and cytoplasm are liquids carrying dissolved substances. Air fills the lungs as gas. The body regulates temperature carefully because its chemistry depends on matter remaining in useful states. Proteins must hold the right shapes. Cell membranes must remain flexible. Water must remain liquid. Too much heat, too much cold, or the wrong pressure can disrupt the delicate material conditions that life requires. Living things are not separate from physics. They are physics arranged into metabolism, memory, movement, and sleep. The same three states also shaped civilization. Solids gave us tools, houses, wheels, roads, writing tablets, pottery, metals, and machines. Liquids gave us rivers for transport, water for agriculture, oils, medicines, inks, dyes, and countless chemical processes. Gases gave us fire, breath, weather, wind power, steam engines, combustion, balloons, refrigeration, and eventually the understanding needed for modern chemistry and physics. Human history is, in one sense, the history of learning how to persuade matter to change state at the right time. Melt the ore, cast the metal, boil the water, condense the vapour, dry the clay, fire the brick, chill the food, pressurize the gas. We have built entire societies by learning the habits of particles we cannot see. And yet, for all this usefulness, solids, liquids, and gases are only the beginning. They are the states that make sense at ordinary temperatures and pressures in the narrow, comfortable band where humans live. Step outside that band and the familiar categories begin to widen. Heat a gas enough, and the atoms themselves start to lose electrons. The gas becomes charged, responsive to electric and magnetic fields, able to glow, arc, and twist in ways ordinary gas cannot. This is where plasma enters the story. It is sometimes called the fourth state of matter, but that phrase can make it sound like an extra item reluctantly added to the end of a list. In truth, plasma is everywhere on the cosmic scale. It fills stars, dances in lightning, shimmers in auroras, and appears in neon signs and fluorescent lamps. The familiar three belong mostly to our cool planetary neighbourhood. Plasma belongs to the universe at large. Before moving toward that brighter and more restless state, it is worth resting for a moment with what the familiar three have taught us. A solid is not simply hard stuff. It is matter whose particles are held in place strongly enough to preserve shape. A liquid is not simply wet stuff. It is matter whose particles remain close but can slide and flow. A gas is not simply invisible stuff. It is matter whose particles move freely and spread to fill space. These states are different answers to the same basic question. How free are the particles to move, and how strongly are they held together? That simple question carries us much farther than it first appears. It links the ice in a glass to the clouds overhead, the breath in your lungs to steam above a kettle, the stone beneath a mountain path to molten rock below the crust. It shows that the material world is not a collection of fixed things, but a constant negotiation between motion and attraction, heat and structure, freedom and form. The table holds still because its particles are bound into place. The water flows because its particles can rearrange. The air surrounds you because its particles are free to wander. And with enough energy, even those wandering particles can be pushed into a stranger condition, one that glows, conducts, responds to fields, and reminds us that matter has more to say once ordinary gas is no longer the end of the road. To reach plasma, we begin with gas, because gas is already halfway to freedom. In a solid, the particles are held in place, vibrating in their little neighbourhoods like guests at a very crowded dinner who have accepted that nobody is getting past the chairs. In a liquid, the particles stay close but can slide around one another, shifting and flowing, finding the shape of whatever holds them. In a gas, the particles are far more independent. They rush about, collide, spread out, and fill the space available to them. A gas is matter with room to roam. But if you keep adding energy, if you heat that gas until its particles move with enough violence and impatience, something deeper begins to happen. The atoms themselves start to come apart at the edges. Electrons are knocked loose. The gas becomes a mixture of charged particles. It begins to respond strongly to electric and magnetic fields. It may glow. It may arc. It may twist into filaments and streams. At that point, the ordinary gas has crossed into plasma. Plasma is often called the fourth state of matter, which makes it sound as if it were standing politely after solids, liquids, and gases in a classroom line. But that phrase hides its true importance. Plasma is not some rare extra condition found only in a laboratory corner with warning labels and someone in goggles saying, "Please do not touch that." Plasma is the most common state of visible matter in the universe. Stars are made of plasma. Vast clouds between stars can be plasma. Lightning is plasma. Auroras are plasma glowing high above Earth. The solar wind is plasma streaming outward from the sun. If you look up at the night sky and see the stars, you're looking at plasma from unimaginable distances, arriving as gentle points of light in your eyes. The solid ground beneath you may feel like the normal state of matter, But across the cosmos, the universe is much more fond of glowing charged seas than of wooden tables and ceramic mugs. This is one of those scientific reversals that feels quietly humbling. To us, plasma seems exotic because we do not usually hold it in our hands, and it is wise that we do not. Most of our daily life is cool enough and calm enough for atoms to remain intact. The electrons stay bound to their atoms. The atoms gather into molecules, crystals, liquids, gases, tissues, clouds, and cups of tea. But in stars, temperatures are so extreme that atoms cannot keep their electrons in the usual way. Matter becomes a restless mix of free electrons and positively charged ions, all moving, colliding, and interacting. Plasma is what matter becomes when ordinary atomic neatness can no longer survive the heat. It can be tempting to think of plasma simply as very hot gas, but that is not quite enough. A very hot gas may become plasma, but plasma has behaviour that makes it different from an ordinary gas. The key is electrical charge. In a normal gas, most atoms and molecules are neutral. They do not have an overall electric charge. They can collide and bounce and spread out, but they do not collectively respond to electric and magnetic fields in the dramatic way charged matter does. In plasma, many particles are charged, and because charged particles influence one another over distances, the whole material can behave as a collective system. It is not just a crowd of particles bumping around. It is a crowd where everyone is tugging, pushing, and responding through invisible electric and magnetic connections. The result is matter that can flow like a fluid, but also conduct electricity, generate magnetic fields, form waves, and shape itself into glowing structures. You have seen plasma, even if you have never called it by that name. Lightning is perhaps the most dramatic local example. During a storm, electrical charge builds between clouds and the ground, or between different parts of a cloud. When the difference becomes large enough, the air itself breaks down. Electrons are stripped from atoms and molecules along a narrow path, turning that channel of air into plasma. For a brief moment, the sky opens with a blinding line of charged matter. The temperature along the lightning channel becomes extremely high, the air expands explosively, and that rapid expansion creates thunder. So the flash and the rumble are both part of the same event. Plasma writes a bright signature across the sky, and the atmosphere answers with sound. There is something almost ancient about lightning. Long before humans understood charged particles, they knew the sky could split with fire. It must have seemed like anger, warning, magic, or the speech of gods. Today we can describe it in terms of electric fields, ionized air and rapidly heated gas, but the description does not make it less wondrous. If anything, it makes it more wondrous. The air around us, normally soft and invisible, can become for an instant a glowing conductive pathway. The ordinary atmosphere can be transformed by energy into something fierce enough to tear bark from trees and illuminate entire landscapes. Plasma is not just out there in stars, it visits Earth in sudden, brilliant lines. Fire is a little more complicated. People often say fire is plasma, but ordinary candle flame is not usually plasma in the same strong sense as lightning or the sun. A flame is hot glowing gas produced by chemical reactions. It may contain a small number of charged particles, and under some conditions parts of a flame can have weak plasma-like properties. But most everyday flames are better understood as combustion, hot gases, soot particles, and light from excited molecules and atoms. This is a nice example of how science gently resists simple labels. Fire looks like it should be a state of matter all by itself, flickering and living and refusing to hold shape. But it is really a process, a chemical transformation producing heat and light. Plasma can glow like flame, and flame can contain some ionized particles, but they are not the same thing in every case. Nature enjoys overlapping appearances just enough to keep us paying attention. Neon signs give a more controlled and familiar kind of plasma. Inside the glass tube, gas is kept at low pressure. When electricity passes through it, some atoms become excited or ionized, and as they return to lower energy conditions, they release light. Different gases produce different colours. Neon gives its famous warm glow, while other gases and coatings can create many hues. A sign outside a diner, a glowing decoration in a window, or the soft-coloured tube in an old city street is not merely light trapped in glass. It is matter in an energised state, a little controlled plasma performing for human eyes. Plasma can be violent in lightning, but it can also be delicate and steady, humming quietly in a tube as people walk past thinking mostly about dinner. Fluorescent lamps and some kinds of street lighting also rely on plasma. Inside the lamp, electricity excites a low-pressure gas. That gas emits ultraviolet light, which then causes a coating on the inside of the tube to glow visibly. The process may seem ordinary because lamps are ordinary, but it is a small technological miracle. Humans learned how to take a gas, energize it into a plasma-like condition, manage the light it produces, and turn that into something as practical as lighting a kitchen or an office. Of course, office lighting has not always used this miracle in the most flattering way, but the physics is still impressive. Auroras are among the most beautiful natural plasmas we can see from Earth. High above the ground, charged particles from the Sun are guided by Earth's magnetic field toward the polar regions. There they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to emit light. The result is the shimmering green, red, violet and pale curtains that ripple across northern and southern skies. An aurora is not paint on the heavens. It is a conversation between the Sun and Earth's magnetic shield. Plasma from the Sun meets the upper atmosphere, and the atmosphere glows back. The sight is quiet from the ground, but physically it is dynamic, full of particles, fields, collisions and energy, arriving from 93 million miles away. The Sun itself is the great plasma presence in our lives. It looks from Earth like a smooth, bright disk, calm enough to be drawn by children as a yellow circle with friendly rays. But the Sun is not calm. It is a vast sphere of hot plasma, roiling with motion, threaded by magnetic fields, rising and sinking in great currents, erupting with flares, sending charged particles outward into space. Its visible surface is not solid. It is a layer of glowing plasma. Above it, loops of plasma follow magnetic field lines, forming arches far larger than Earth. Sunspots appear as darker regions where magnetic activity changes the flow of heat. Solar flares and coronal mass ejections can throw enormous amounts of plasma and radiation into space. From our safe distance, sunlight is warm and gentle on a face. Up close, the Sun is matter in an extreme and restless state. This solar plasma matters to us in very practical ways. The Sun supplies nearly all the energy that supports life on Earth. It drives climate, weather, photosynthesis, ocean currents, and the daily rhythm of light and darkness. But its plasma activity also affects technology. Strong solar storms can disturb satellites, radio communication, navigation systems, and power grids. The same star that warms a garden can send charged particles racing through space, rattling Earth's magnetic environment like a hand shaking a bell. The fact that we can predict and study this space weather at all is part of modern plasma physics. We are not just studying distant stars for beauty. We are studying the changing plasma environment that our planet lives inside. Plasma also appears in human technology in more intense forms. Welding arcs use plasma to generate extreme heat, allowing metals to melt and join. Plasma cutters slice through metal by creating a high-energy jet of ionized gas. Industrial plasma processes can etch surfaces, sterilize equipment, treat materials, and help manufacture electronics. In some devices, plasma is used to create conditions that no ordinary flame or mechanical tool could manage. It is strange to think that the same broad state of matter found in stars is also used in factories, workshops, laboratories, and medical tools. The universe often gives us grand phenomena first, and then, after much patience and engineering, we learn how to make smaller, carefully behaved versions of them on Earth. One of the great dreams involving plasma is controlled fusion power. Fusion is the process that powers stars, where light atomic nuclei join together under extreme conditions and release energy. To make fusion happen on Earth in a controlled way, scientists must create and confine plasma at incredibly high temperatures. The challenge is almost comically difficult. You need matter hotter than the centre of the Sun, but you cannot simply put it in a normal container, because the container would not remain a container for very long. Instead, researchers use magnetic fields or powerful lasers to hold and compress the plasma without letting it touch ordinary walls in destructive ways. It is like trying to hold a piece of starfire in an invisible bottle while asking it politely to power civilization. This is not easy, which is why fusion has taken many decades of research. Plasma is hard to control because it is alive with collective behaviour. It can become unstable. It can wiggle, twist, leak, cool, and form patterns that spoil the conditions needed for fusion. Scientists study these instabilities carefully, learning how plasma responds to magnetic fields, heating, confinement, and turbulence. Every improvement requires deep understanding and extraordinary engineering. Fusion research is, in a sense, the art of negotiating with plasma, persuading charged matter to stay hot, dense, and organized long enough to release useful energy. Whether or not fusion becomes a major energy source soon, the effort has already taught us an enormous amount about one of the universe's most important forms of matter. Plasma can behave in ways that feel almost creature-like. Because it responds to magnetic fields, it can form filaments, loops, sheets, and twisting structures. In space, plasma does not simply drift like ordinary gas. It can be guided and shaped by magnetism. This is why solar prominences form graceful arcs above the Sun. It is why charged particles spiral along magnetic field lines. It's why Earth has radiation belts and a magnetosphere that acts like a protective bubble. Plasma makes space less empty and far more dynamic than the old image of silent vacuum suggests. Space contains fields, particles, streams, shocks, waves, and enormous invisible structures linking stars and planets. Even in the space between galaxies, plasma can exist as extremely thin hot gas. It may be so spread out that by earthly standards it would feel like almost nothing, yet across cosmic distances it becomes important. Galaxy clusters contain huge amounts of hot plasma between their galaxies, glowing in X-rays because of its extreme temperature. This intracluster medium, as scientists call it, can contain more ordinary matter than the galaxies themselves. Imagine that. The visible galaxies, with their stars and worlds and possible civilizations, are embedded in an enormous bath of thin, hot plasma. Once again, matter refuses to arrange itself according to human intuition. The bright islands are not the whole ocean. The early universe was also a plasma. For a long time after the beginning, matter was too hot for atoms to form in the way they exist today. Electrons and nuclei moved freely in a dense glowing state, scattering light constantly. The universe was opaque, not because it was dark, but because it was too full of charged particles for light to travel freely. Only after it expanded and cooled enough could electrons settle with nuclei into neutral atoms. Then light could move across space more freely. That ancient light still exists today as the cosmic microwave background, a faint relic from the time when the universe changed from an ionized plasma into a transparent cosmos filled with neutral atoms. Every time cosmologists study that background glow, they are reading a message from the period when matter changed its state on the largest possible stage. There is a wonderful symmetry in this. Plasma belongs both to the early universe and to the stars that later formed within it. It appears at the beginning of cosmic history, and then again in the engines that light galaxies. It is present in lightning over a field, in auroras above polar ice, in laboratory chambers, in industrial arcs, in the solar wind, in glowing signs, and in the vast spaces between galaxies. It is at once ordinary and extraordinary, common and difficult, cosmic and practical. The reason it feels unfamiliar is not because it is rare, but because human life occupies a cool, dense, quiet corner of matter where atoms are allowed to keep their electrons and behave themselves. So what makes plasma a state of matter rather than just a hot mess of particles? The answer is that plasma has collective behaviour. Its charged particles interact through electric and magnetic forces over larger distances than ordinary particle collisions alone. It can conduct electricity. It can support waves. It can be confined by magnetic fields. It can shield electric fields within itself. It can develop instabilities and structures. These features give it a distinct identity. A gas becomes plasma when enough of its particles are ionized for these collective electromagnetic behaviors to matter. In weakly ionized plasmas, only a small fraction of particles may be charged, but those charged particles can still strongly influence the behavior of the whole system. In fully ionized plasmas, atoms are stripped down much more completely. The details vary, but the theme remains the same. Charge changes everything. You can think of a neutral gas as a room full of people wandering independently, occasionally bumping shoulders and changing direction. A plasma is more like a room where many of those people are holding invisible elastic threads connected to one another and to the walls. When one moves, others respond. Patterns can travel through the crowd. Waves can form. The whole room becomes coordinated in strange ways. This is not a perfect picture, but it gives the feeling. Plasma is matter with long-distance electrical conversation built into it. The colours of plasma can be beautiful, but they are not decoration. They come from the way atoms and ions interact with energy. When electrons in atoms or ions gain energy and later release it, they emit light at characteristic colours. This is how scientists can study the composition of stars and nebulae. The light from plasma carries fingerprints of the elements within it. A distant star may be far beyond our reach, but its light can tell us what it is made of, how hot it is, how fast it is moving, and what physical conditions exist in its atmosphere. Plasma becomes readable. The glow is not just brightness, it is information crossing space. That may be one of the most poetic facts we can mention without becoming too poetic about it. The stars are not merely shining, their plasma is sending messages. Every colour and line in their light contains clues. Human beings standing on a small rocky planet made mostly of non-plasma matter learn to decode those clues and discover the chemistry of suns. The same kind of matter that forms lightning and auroras also writes the spectral signatures that let us understand the universe. Plasma is not only fiery, it is communicative. Still, plasma is not always hot in the everyday sense. There are plasmas called cold plasmas, where the electrons may be energetic while the heavier particles remain comparatively cool. These can be used in certain medical and industrial applications. The word cold here can be a little misleading, because some parts of the plasma are still energetic, but it shows again that plasma is defined not simply by temperature, but by ionization and collective behaviour. Some plasmas are searingly hot, like stellar interiors. Others are low temperature enough to be used near delicate surfaces. Matter keeps finding ways to complicate our first impressions. As we sit with plasma, the familiar path from solid to liquid to gas begins to look different. It is not merely a sequence of melting and boiling, it is a story of increasing freedom and energy. In solids, particles are constrained. In liquids, they can slide. In gases, they roam. In plasma, the atoms themselves are opened into charged components, and the material enters a new world of fields and currents. The structure is no longer just about where particles sit or how they collide. It is about how charges move together and how electromagnetic forces shape the whole. And yet even plasma is not the final answer to matter. For a long time, the four-state picture felt like a satisfying expansion. Solid, liquid, gas, plasma. There is a rhythm to it, a neatness, a sense that the missing piece had been added. But physics did not stop there. When matter is cooled to temperatures close to absolute stillness, entirely different behaviours emerge. The particles do not merely slow down, they can begin to share a quantum identity in ways that seem almost impossible from the warm perspective of daily life. Matter can become less like a crowd and more like one coordinated presence. It can flow without ordinary friction. It can reveal rules hidden far beneath the scale of cups, clouds, flames, and stars. After the fierce brightness of plasma, the next surprise waits at the opposite extreme, in a cold so deep that motion itself seems to hold its breath. After the fierce brightness of plasma, it may feel natural to keep looking toward hotter and hotter places. Stars, lightning, solar storms, the early universe, all of them remind us that matter changes when energy is poured into it. Heat a solid enough and it melts. Heat a liquid enough and it becomes gas. Heat a gas enough and electrons begin to break free and plasma appears with all its glowing, charged restlessness. But matter has another road it can travel, a road that does not lead upward into fire but downward into stillness. If plasma is matter becoming wild with energy, a Bose-Einstein condensate is matter becoming quiet in a way so extreme that the ordinary separateness of atoms begins to blur. This is where the story becomes very strange, not because matter becomes violent or cosmic, but because it becomes almost too calm to behave like matter as we normally understand it. We're used to thinking of atoms as tiny individual things, each one moving about in its own way, bumping, vibrating, drifting, colliding, obeying the rules of its state. In a solid, they vibrate in place. In a liquid, they slide past one another. In a gas, they rush around freely. But if certain kinds of atoms are cooled to temperatures unimaginably close to absolute zero, something remarkable can happen. Their individual quantum identities begin to overlap. They stop behaving like a crowd of separate particles and begin behaving more like a single shared wave. This is a Bose-Einstein condensate. It is not something you can find naturally in your kitchen, unless your kitchen is equipped with lasers, vacuum chambers, magnetic traps, and a level of cold that would make deep space seem almost warm by comparison. Ordinary cold is not enough. A winter morning is not enough. Liquid nitrogen is not enough. Even the cold emptiness between stars is usually not enough. A Bose-Einstein condensate requires a level of cooling so close to absolute zero that the motion of atoms is reduced almost to its lowest possible limit. Not stopped entirely, because quantum physics does not allow perfect stillness in the old classical sense, but slowed so dramatically that the wave nature of matter becomes impossible to ignore. This idea begins with one of the quieter revolutions in physics. We often talk about particles as if they are tiny little balls, because that image is easy to hold in the mind. A grain of dust, a marble, a planet, a bead, a speck. But quantum mechanics tells us that particles are not simply tiny balls. They also have wave-like properties. Under ordinary warm conditions, atoms move around so quickly and interact so chaotically that this wave nature is not obvious in the everyday world. You do not see a chair spreading out like a ripple. You do not notice your cup of tea behaving like a wave unless you actually shake the cup, in which case the wave is very real and possibly on your trousers. But at extremely low temperatures, atoms slow down, and their quantum wavelengths grow larger. If they become cold enough and crowded enough, those wavelengths can overlap. That overlap is the key. Imagine a room full of people all talking at once, each with their own voice, pace, mood, and story. That is a warm gas, in a very loose way. Now imagine the room becoming quieter and quieter, until instead of many separate voices, the crowd begins to hum the same note together. Not because anyone is forcing them with a conductor and a stern expression, but because the rules of the system allow them to fall into the same state. A Bose-Einstein condensate is not exactly a crowd humming, of course, but the image gives the feeling. Many atoms occupy the same quantum condition, and the collection begins to behave as one. The idea was predicted long before it was created. In the 1920s, the Indian physicist Satyendra Nath Bose developed a new way of thinking about certain particles, especially particles of light. He sent his work to Albert Einstein, who recognized its importance and extended the idea to atoms. Together their names became attached to the strange state of matter that would later be known as the Bose-Einstein condensate. This was not an immediate laboratory discovery. It was a prediction, a quiet mathematical doorway opened decades before technology could walk through it. Physics often works like that. The mind sees a possibility, then the instruments spend years, sometimes generations, trying to catch up. For a long time, Bose-Einstein condensation remained a beautiful idea waiting for the right tools. The problem was cooling. To make atoms enter this shared quantum state, scientists had to remove almost all of their thermal motion. But atoms are small, quick, and stubbornly energetic. You cannot simply put them in a freezer and hope they become quantum philosophers. The cold needed is far beyond anything produced by ordinary refrigeration. Researchers had to develop methods like laser cooling and evaporative cooling. These techniques sound almost contradictory at first. Lasers usually make us think of heat, cutting, burning, or at least dramatic red beams in science fiction corridors, but carefully tuned lasers can actually slow atoms down. They can nudge atoms in ways that reduce their motion, stealing tiny amounts of momentum again and again until the atoms become extraordinarily cold. Then, after laser cooling, scientists can use evaporative cooling, which is a little like what happens when the hottest molecules leave a cup of coffee and the remaining liquid cools slightly. In the laboratory version, the most energetic atoms are allowed to escape from a trap, leaving the colder atoms behind. Repeat this carefully, and the remaining cloud becomes colder and colder. It is a process of selecting stillness, of letting the restless ones leave until the calmest atoms remain. There is something almost bedtime appropriate about that, though the equipment involved is somewhat less cozy than a blanket. The first successful Bose-Einstein condensates in dilute atomic gases were created in 1995, using rubidium atoms and then sodium atoms in separate experiments. This was a major achievement because it brought a state of matter predicted decades earlier into direct observation. A small cloud of atoms cooled to a tiny fraction of a degree above absolute zero suddenly showed the behavior physicists had been seeking. The atoms entered the same quantum state. A new form of matter, or at least a new accessible state of matter, had been made in the laboratory. It was not glowing like plasma. It was not pouring like water. It was not rigid like ice. It was a delicate quantum object, a cloud of matter behaving with an eerie unity. It is easy to miss how astonishing that is. The atoms were still atoms. They had not been crushed into neutron star material. They had not been broken apart into quark-gluon plasma. They were not inside a star or at the beginning of the universe. They were ordinary atoms handled with extraordinary care. Under the right conditions, those ordinary atoms revealed behavior hidden by the warmth and noise of normal life. This is one of the recurring lessons of matter. Change the conditions, and matter shows you a new side of itself. Not because it has become magical, but because physics has different rules waiting at different scales. At room temperature, atoms in a gas behave like individuals. They zip around at different speeds in different directions with their own little histories of collisions. If you could track them, which would be a heroic and probably exhausting task, each atom would have a separate story. In a Bose-Einstein condensate, many atoms share the same lowest energy state. The cloud becomes coherent, meaning its matter waves are lined up in a coordinated way. Coherence is also important in lasers, where light waves march together rather than randomly. A Bose-Einstein condensate is sometimes compared to a laser made of atoms, though like all comparisons, it is helpful only if you do not lean on it too heavily. The main point is that the atoms lose much of their individual disorder and begin acting collectively. This collective behaviour allows scientists to observe quantum effects on a scale larger than individual atoms. Usually quantum mechanics hides from us because its weirdness is strongest at tiny scales and gets washed out in large warm systems. A Bose-Einstein condensate lets researchers bring quantum behaviour into a cloud big enough to study with carefully designed instruments. It is still tiny by everyday standards, but enormous compared with a single atom. It is like persuading the quantum world to step onto a slightly larger stage, though still under very strict lighting and temperature requirements. One of the strange things about a Bose-Einstein condensate is that it can flow in unusual ways. It is closely related to the physics of superfluidity, where a fluid can move without ordinary viscosity. Not every Bose-Einstein condensate is simply the same thing as a superfluid in every context, but the connection is deep. In these ultra-cold systems, atoms can move collectively with very little resistance, and the flow can reveal quantum patterns such as vortices. A vortex in an ordinary liquid can take many forms, like water swirling down a drain. In a quantum fluid, rotation is restricted in special ways. The vortices come in distinct units, not arbitrary amounts. The fluid is not just swirling however it likes, it follows quantum rules. These quantum vortices have been observed in Bose-Einstein condensates. Scientists can stir the condensate with laser beams or manipulate it with fields, creating tiny whirlpools in the cloud. That may sound delicate, and it is, but it is also profound. A little ultra-cold cloud in a laboratory can act as a model system for studying physics that appears in other places, from superconductors to neutron stars. The same mathematical ideas can echo across very different systems. A small trapped condensate on Earth can help researchers understand how quantum matter behaves under conditions that would otherwise be inaccessible. Sometimes the universe lets us study vast mysteries by making small, carefully controlled cousins of them in a lab. The phrase "when matter becomes almost one" is not just a poetic flourish, it points to the central oddness of this state. In everyday life, individuality seems obvious. One grain of sand is not the same as another. One drop of water can merge with another drop, but the molecules inside are still buzzing around in many different states. In a Bose-Einstein condensate, the atoms become described by a shared quantum wave function. Again, we do not need equations here. The idea is that the atoms are no longer best understood as entirely separate little objects, each with its own independent quantum description. The whole cloud has a shared description. It is many particles, yet one state. This does not mean the atoms have literally fused into a single giant atom. They remain atoms. They can be counted in principle. If the condensate is disturbed or warmed, the shared state breaks apart and the atoms return to more ordinary behaviour. The unity is conditional and delicate. It exists only while the environment is cold and controlled enough to protect it. Heat is the great disruptor. Thermal motion scrambles coherence. A little warmth brings back individuality, randomness, and ordinary gas behaviour. In that sense, a Bose-Einstein condensate is like a whisper that can only be heard when the room is almost perfectly silent. Absolute zero itself is a boundary that cannot be reached exactly, only approached. It represents the lowest possible temperature, where a system has the minimum thermal motion allowed by quantum physics. The closer you get, the more unusual matter can become. The atoms no longer have enough energy to populate many different states, so they crowd into the lowest available one. For particles known as bosons, this crowding is allowed. That is important. Quantum particles come in different families, and bosons have the special ability to share the same quantum state. They are sociable in a way that another family of particles called fermions is not. Fermions obey rules that prevent identical particles from occupying exactly the same state. Bosons, on the other hand, are perfectly content to gather together in the same condition, like sleepy guests all deciding the same sofa is the best place in the room. This difference between bosons and fermions is one of the deep organizing principles of matter. It explains why electrons arrange themselves in atoms the way they do. why matter has structure, and why certain particles can form condensates. Atoms made from an even number of fermionic components can behave as bosons overall, which is why certain atoms can form Bose-Einstein condensates. This sounds technical, but the essential idea is gentle enough. Some particles are allowed to pile into the same quantum state, and under extreme cold they do exactly that. Matter follows the permissions written into quantum mechanics. A Bose-Einstein condensate is fragile not only because it needs extreme cold, but also because the atoms must be isolated from the surrounding world. Warm walls, stray particles, vibrations, radiation, and imperfections can disturb it. This is why experiments use vacuum chambers and magnetic or optical traps. The atoms are held without touching ordinary surfaces. They float in carefully arranged fields, suspended like a tiny cloud of near stillness. Scientists then probe the condensate using light and imaging techniques, often releasing it from the trap and letting it expand so they can observe the telltale pattern of condensation. The entire process requires patience, precision, and an impressive ability to make nature calm down. Why go to all this trouble? Because Bose-Einstein condensates are more than curiosities. They are tools for exploring quantum mechanics, precision measurement, atomic behavior, superfluidity, and the boundary between microscopic and macroscopic physics. They can help scientists test fundamental theories, simulate other quantum systems, and build sensitive instruments. Atom interferometers, for example, can use matter waves to measure acceleration, rotation, gravity, and other effects with great precision. A condensate can be part of a device that senses tiny changes in the world, not by gears or springs, but by the wave nature of matter itself. There are also optical lattices, where laser light creates a patterned landscape that atoms can sit in, almost like eggs in a carton made of light. When Bose-Einstein condensates are placed in these lattices, scientists can study how atoms behave in controlled artificial crystals. This can help model materials that are otherwise difficult to understand, including systems related to magnetism, superconductivity, and strongly interacting quantum matter. In a sense, researchers can build simplified universes for atoms, then watch how quantum rules play out. It is one of the more elegant tricks of modern physics. Instead of only studying matter found in nature, we create conditions where matter can teach us in a cleaner language. The discovery of Bose-Einstein condensates also changed the way people thought about states of matter. The old categories were based mostly on visible behavior. Solids hold shape, liquids flow, gases expand, plasma conducts and glows because it is ionized. But a Bose-Einstein condensate is defined by quantum organization. You cannot understand it simply by looking at whether it holds a shape or fills a container. Its identity lies in the shared quantum state of its atoms. This expands the meaning of state of matter. A state is not only about everyday appearance. It can be about deeper order, symmetry, coherence, and collective behavior. That is why the question of how many states of matter exist becomes harder the farther we travel. We're no longer just naming the things children can touch and paw. We're naming patterns of organization that appear only under extreme or carefully prepared conditions. Some states exist naturally in stars. Some exist in the cores of dead stars. Some existed in the infant universe. Some are made in laboratories for fractions of a second, or held in traps while scientists take measurements. If matter can enter a distinct pattern of behavior with its own rules, physics may treat it as a state or phase. The list grows not because scientists are trying to make things complicated, but because matter really does have many ways to be itself. A Bose-Einstein condensate also forces us to rethink what it means for matter to be cold. In ordinary language, cold is about sensation. A cold glass, cold air, cold hands, cold feet under a blanket causing negotiations between partners at bedtime. But in physics, temperature is tied to the motion and energy of particles. Cooling is not just making something feel chilly. It is reducing the random motion of the particles. At the extreme cold needed for condensation, atoms slow so much that their wave nature spreads out. Cold becomes not just the absence of warmth, but the doorway to quantum unity. That is a beautiful reversal. At high heat, matter becomes ionized and collective through charge. At extreme cold, matter becomes collective through coherence. Plasma and Bose-Einstein condensate sit like opposites in the story. Plasma is hot, energetic, charged, common across the stars. A Bose-Einstein condensate is ultra-cold, delicate, neutral in many cases, rare outside laboratories. Plasma fills the visible universe. Condensates must be coaxed into existence with careful instruments. Plasma is bright and restless. A condensate is dim and quiet. Yet both reveal that matter is capable of collective behavior beyond the familiar three states. In plasma, particles respond together through electromagnetic fields. In a condensate, atoms share a quantum state. Both are reminders that matter is not merely a pile of tiny things. Under the right conditions, it becomes organized as a whole. There is a gentle lesson here about scale. The everyday world encourages us to think that reality is built from separate objects. A cup, a table, a hand, a breath, a star in the sky. But physics keeps finding levels where separateness becomes less obvious. In a solid crystal, atoms form a repeating structure. In a liquid, molecules move together in flows. In plasma, charged particles create collective waves and fields. In a Bose-Einstein condensate, atoms share a quantum identity. The universe does not always begin with isolated things and then build connections. Sometimes the connection is the best description. Still, we should be careful not to turn this into mystery for mystery's sake. A Bose-Einstein condensate is strange, but it is not magic. It does not mean consciousness creates matter, or that atoms decide to become one in a sentimental way. It is a physical state predicted by quantum theory, produced in laboratories, measured with instruments, and used for research. Its wonder is stronger when we keep it real. The universe does not need exaggeration. It is already astonishing enough that cooling a gas of atoms to near absolute zero can make thousands or millions of them occupy one quantum state and behave like a single matter wave. Imagine for a moment a cloud so cold that its atoms barely wander. It is held in a trap, isolated from the warm, noisy world. The atoms have been slowed and selected, cooled and gathered until many of them fall into the same lowest state. The cloud is not large. It's not something you would notice across a room. But inside it, matter is demonstrating a rule far deeper than ordinary touch can reveal. The atoms are no longer behaving like a random gas. They are moving under a shared quantum description. It is a quiet state, almost shy compared with lightning or the sun. But in that quietness, it shows us something extraordinary. Matter can become coordinated not by force, not by chemical bonding, not by solid structure, but by quantum sameness. And once that door is open, other strange forms wait nearby. Ultra-cold matter leads naturally into questions about superfluids, superconductors, and supersolids, where flow, resistance, and structure behave in ways that defy everyday expectation. A liquid that can climb walls or flow without ordinary friction. A material that can carry electric current without losing energy. A state that seems to combine the order of a solid with the frictionless motion of a superfluid. These are not science fiction decorations added to physics for dramatic effect. They are real examples of matter discovering loopholes in the rules we thought were obvious. The familiar world has friction, viscosity, resistance, and drag. But in the cold quantum world, some of those everyday obstacles begin to fade, and matter moves with a smoothness that feels almost impossible from the warm side of reality. The cold quantum world has a way of making ordinary common sense feel a little underdressed. In the warm world around us, matter has friction, resistance, drag, roughness, stickiness, and all the little inconveniences that make the universe feel properly solid and practical. Push a chair across the floor and it resists. Stir honey and it clings to the spoon. Pour water through a narrow tube and it loses energy as it rubs against the walls. Spin a cup of coffee and the swirling gradually slows down. The everyday world is full of motion that fades, flow that struggles, and energy that quietly leaks away as heat. This is so normal that we barely notice it. Matter, as we meet it in daily life, is always being slowed by something. Then comes the strange world of superfluids, where some of that ordinary resistance seems to vanish. A superfluid is a fluid that can flow with no ordinary viscosity. Viscosity is the internal friction that makes liquids resist flowing. Water has low viscosity and pours easily. Honey has higher viscosity and pours as if it would rather finish its thoughts first. Tar can flow so slowly that it seems almost solid to human patience. But a superfluid is stranger than simply being thin. It is not just a very runny liquid, it is matter in a quantum state, where flow can happen without the usual friction that drains motion away. It can move through tiny channels, it can form persistent currents that keep circulating. It can behave in ways that make the familiar boundary between liquid and quantum object feel suddenly porous. The most famous superfluid is helium cooled to extremely low temperatures. Helium is already an unusual substance. It is a light noble gas under ordinary conditions, drifting invisibly, famous for making balloons float and voices briefly sound as if they belong to cheerful cartoon characters. But cool helium enough, and it becomes a liquid. Cool one common form of liquid helium even further, and it enters a superfluid state. This transition is not like water freezing into ice. It is not a simple change from flowing to rigid. Instead, the liquid remains liquid, but its internal behavior changes deeply. It becomes a quantum fluid, a liquid whose large-scale motion reveals rules normally hidden at the tiny scale of atoms. One of the most startling things about superfluid helium is that it can creep along surfaces in a thin film. If placed in a container, it can climb up the walls, cross the rim, and flow down the outside as if the liquid has quietly decided that containers are only suggestions. This does not mean it is alive or mischievous, though one can understand why early demonstrations had that feeling. It happens because the superfluid film can move with almost no resistance along surfaces, driven by subtle forces and its own quantum behavior. To anyone expecting a normal liquid to stay politely inside the bowl, it looks as if matter has broken an agreement. There is also the fountain effect. When superfluid helium is heated in a certain arrangement, it can shoot upward in a jet, almost like a tiny cold fountain. The effect comes from the way heat and flow are connected in the superfluid state. Again, it is not magic, but it is not what warm intuition expects. Ordinary liquids conduct heat and flow in familiar ways. A superfluid can carry heat with astonishing efficiency, not because its atoms are rushing around like a boiling pot, but because the collective quantum state allows energy to move through it in a special manner. It is one of those phenomena where the explanation is physical and precise, yet the image remains wonderfully strange. A liquid colder than almost anything in nature can rise in a little fountain because heat nudges its quantum order in just the right way. To understand why superfluidity is so unusual, it helps to return to the idea of collective behavior. In a normal liquid, particles move in a crowded, disordered fashion. They collide, jostle, and exchange energy. When the liquid flows, its layers rub against one another and against surfaces. That rubbing is viscosity. It turns organized motion into heat. Stir a liquid and the swirling gradually dies because energy is scattered into microscopic disorder. But in a superfluid, part of the liquid enters a shared quantum state. The particles no longer behave entirely like independent little travelers. Their motion becomes coordinated in a way that ordinary particle pictures cannot fully capture. The fluid can move as a whole, with no available low-energy way to scatter and lose motion under certain conditions. This does not mean a superfluid can do absolutely anything without resistance. Real systems have limits. If the flow becomes too fast, or if disturbances are strong enough, the superfluid can create excitations, vortices, and other forms of motion that carry energy away. But below certain limits, it can flow without ordinary viscosity. This is why superfluidity is so important. It reveals that friction is not simply an unavoidable feature of all matter. It depends on the state of the system and the rules available to it. Under the right quantum conditions, matter can move in a way that seems almost too smooth for the world we know. A superfluid also rotates in a strange way. If you rotate an ordinary bucket of water, the water tends to rotate with the bucket. It can swirl in a continuous range of ways, forming a curved surface as it spins. A superfluid cannot simply rotate like an ordinary liquid. Rotation enters through quantized vortices. That word sounds technical, but the image is clear enough. Instead of the fluid spinning smoothly in any amount it likes, it forms tiny whirlpools with specific allowed amounts of circulation. These vortices are like little quantum tornadoes, each one carrying a fixed unit of rotational motion. The fluid does not negotiate its rotation continuously. It accepts it in counted pieces. This is a deeply quantum idea made visible in a fluid. The word quantum itself points to the fact that certain physical properties come in discrete amounts, not just any value whatsoever. In the warm, everyday world, this discreteness is usually hidden. A car can seem to move at any speed. A wheel can seem to turn at any rate. A river can swirl in any strength. But in a superfluid, the quantum rules rise to a scale we can observe. The whirlpools are not arbitrary. They are signatures of the underlying wave nature of the fluid. It is as if the liquid is quietly saying, "I am not just stuff, I am a wave obeying rules." Superfluidity is closely connected to the Bose-Einstein condensate we just visited. In some systems, many particles enter a shared quantum state, and that shared state supports frictionless flow. Liquid helium is more complicated than the dilute atomic gases used in many condensate experiments because its atoms interact strongly, but the theme is similar. When enough of the system becomes quantum coherent, the behavior of the whole changes. Matter begins to act less like a crowd of separate particles and more like a coordinated field. That coordination allows motion that ordinary liquids cannot sustain. There is another kind of helium, helium-3, that can also become superfluid, but by a different route. Helium. 3 atoms belong to the family of particles that cannot all pile into the same quantum state in the simple way bosons can. To become superfluid, they pair up under very cold conditions, forming pairs that can behave collectively. This pairing is related in spirit to what happens in superconductors, where electrons pair up and electrical resistance disappears. The details are different, but the resemblance is beautiful. Quantum particles that cannot move together alone can sometimes form pairs that enter a shared state. The universe, when blocked by one rule, occasionally finds another door. Superconductivity is not exactly the same as superfluidity, but the comparison is useful. In a superconductor, electric current can flow with no electrical resistance. In a superfluid, matter itself can flow with no ordinary viscosity. Both phenomena show that resistance is not inevitable under all conditions. Both depend on collective quantum behavior. Both are usually associated with low temperatures, though scientists continue searching for and creating materials where these effects happen under less extreme conditions. Both have transformed the way physicists think about matter, not as a set of individual particles moving independently, but as a system capable of falling into shared patterns with entirely new properties. In the ordinary world, friction and resistance are so reliable that they feel like part of reality furniture. Without friction, walking would be difficult, writing would be nearly impossible, and placing a cup on a table might become a very tense event. But friction is also a sign of disorder being produced. Motion becomes heat. Energy spreads. Things slow. Superfluids and superconductors show what happens when quantum order prevents some of that spreading. The motion does not decay in the usual way because the system has no easy path for turning that motion into random internal disturbance. It is not that the superfluid is ignoring physics, it is following physics more strictly than ordinary matter allows us to notice. Then we arrive at the even stranger idea of a supersolid. The name sounds almost like a contradiction, like dry water or silent thunder. A solid, by ordinary definition, has structure. Its particles are arranged in a pattern and hold their positions. A superfluid, by contrast, flows without ordinary viscosity. How can matter be both solid and superfluid? How can it have a rigid arrangement and yet allow frictionless flow? This is exactly why supersolids have fascinated physicists for so long. They suggest a state where matter keeps a kind of crystalline order while also displaying superfluid behaviour. It is as though part of the material says, "I will stay arranged," while another part says, "I will move without resistance," and somehow both voices belong to the same system. For many years, supersolidity was mostly a theoretical possibility. Physicists wondered whether certain forms of solid helium might contain defects or quantum motion that allowed part of the material to flow through the rest. Experiments were difficult, and interpretations were controversial. Some results seemed to suggest supersolid behaviour, then later explanations showed that ordinary mechanical effects might be involved. This is a healthy part of science, even if it is less dramatic than a clean discovery story. Nature gives a hint. Scientists get excited. More careful experiments ask whether the hint is real. Sometimes the answer is yes. Sometimes it is not that simple. The universe does not always label its clues clearly. More recent work with ultra-cold atomic gases has allowed scientists to create states that show supersolid-like behaviour in a clearer and more controllable way. In these systems, atoms can form a patterned density structure, something like a crystal, while still maintaining phase coherence associated with superfluidity. Instead of relying on ordinary solid helium, researchers can use trapped atomic clouds where interactions are tuned and observed with great precision. These laboratory supersolids are delicate and specialised, but they bring the idea into view. Matter can arrange itself in a repeating pattern and still keep the quantum connectedness needed for superfluid flow. The contradiction begins to soften. Solid order and superfluid motion are not always enemies. To imagine this, think of a marching band where everyone is standing in a repeating pattern across a field, but the music itself flows through them as one continuous coordinated wave. The people are arranged, yet the shared performance moves. That image is not exact, but it captures the feeling. In a supersolid, density may be modulated in space, meaning some regions contain more atoms and some fewer in a regular pattern, while the quantum state remains coherent across the system. There is structure, but also unity. There is position, but also flow. It is one of those states that reminds us that everyday opposites are often just limitations of everyday experience. Supersolids matter because they challenge our instinctive categories. We think of solids as fixed and fluids as flowing. We think of order and motion as different kinds of behaviour. But quantum matter can combine features that seem incompatible. The deeper language is not simply solid versus liquid. It involves symmetry, coherence, correlations, and collective states. A crystal breaks the continuous symmetry of space by choosing a repeating pattern. A superfluid has a coherent phase that allows frictionless flow. A supersolid has both kinds of order at once. We do not need to dwell on the formal language, but the idea is powerful. Matter is not limited to one form of organisation at a time. Under the right conditions, it can layer orders together. This makes superfluids and supersolids part of a broader world called condensed matter physics, which studies how many particles together create new behaviour. The phrase condensed matter may sound modest, perhaps like something stored carefully in a cupboard, but it is one of the richest areas in physics. It includes crystals, magnets, superconductors, semiconductors, liquid crystals, topological materials, superfluids, and many other states and phases. The central lesson is emergence. When many particles interact, the whole can behave in ways that are not obvious from the particles alone. A single helium atom is not superfluid. A cloud or liquid of helium atoms under the right conditions can be. A single electron is not a metal. Many electrons moving through an atomic lattice can make a conductor, an insulator, a magnet, or a superconductor. The collective is not just a larger version of the individual, it can be something new. This is why states of matter are not merely a childhood list. They are an active frontier. Every time scientists learn how to cool, compress, trap, tune, layer, or excite matter in a new way, there is a chance of finding a new phase. Some phases are dramatic and easy to picture. Plasma glows. Superfluids climb and flow strangely. Others are hidden in measurements, revealed through how a material conducts, responds to fields, stores energy, or changes symmetry. The state of matter may not announce itself visually. It may whisper through resistance, heat capacity, magnetic response, or a pattern in scattered light. Modern physics is partly the art of learning how to hear those whispers. There is something restful, oddly enough, about superfluidity. It is motion without the usual grinding, flow without the familiar loss, a current that can persist. In the warm human world, everything runs down. A spinning coin falls, a stirred cup settles, a moving object slows, a battery drains, a day tires us out, but a superfluid shows a special pocket of reality where motion can continue in a purer way, protected by quantum order. It does not defeat entropy in some grand cosmic sense, and it does not make perpetual machines possible for everyday life. But it gives us a glimpse of a different kind of movement, one with fewer of the rough edges that define our ordinary experience. Supersolids, meanwhile, offer a different kind of wonder. They suggest that matter can hold still and flow at the same time, if we understand those words carefully enough. They show that a material can possess internal structure while still allowing a shared quantum motion through it. This makes them feel almost paradoxical, but the paradox belongs mostly to our language. The quantum world is not required to obey the categories invented from human hands and kitchen tables. It has its own grammar. Sometimes that grammar allows sentences we would never have written ourselves. If you return in your imagination to the room around you, the contrast becomes gentle and clear. Your blanket has friction. The fibers catch and fold. The mattress supports weight through ordinary solid structure. The air flows, but not without resistance. The water in a glass would stop swirling soon after being stirred. Everything nearby belongs to the warm, practical, resistant world. It is a good world. It lets us stand, sleep, build, cook, and keep books on shelves. But hidden beyond ordinary temperature, matter has quieter and stranger possibilities. Cool it enough, arrange it carefully enough, and it begins to reveal patterns where friction fades, currents persist, and the old categories become less firm. These states are not common in daily life because they are fragile. Warmth destroys the delicate quantum coherence they need. A little thermal noise is enough to return the system to more ordinary behaviour. This fragility makes them precious as laboratory objects. Scientists must isolate them, cool them, protect them, and measure them before the outside world intrudes. There is almost a tenderness in that. To see matter break the rules, one must first create conditions gentle enough for the deepest rules to show themselves. The quantum world does not shout over the noise, it waits for silence. And once we have seen superfluids and supersolids, the question of how many states of matter exist becomes even less like a number and more like a map expanding in the dark. We began with the familiar three. We moved to plasma, the charged fire of stars. We descended into Bose-Einstein condensates, where atoms become almost one. Now we have seen fluids that lose ordinary viscosity, and solids that may carry superfluid order within structure. Matter is no longer just shape, volume, and flow. It is coherence, resistance, symmetry, collective motion, and hidden order. The next step takes us away from laboratory cold and into crushing weight, where matter is not gently cooled into unity, but squeezed by gravity until atoms themselves can no longer remain the kind of atoms we know. Matter can become strange when it is cooled almost to stillness, but it can become just as strange when it is crushed beyond ordinary imagination. Cold reveals one hidden side of the quantum world. Gravity reveals another. In the laboratory, scientists gently trap atoms, cool them, and persuade them into delicate shared states. In dying stars, there is nothing gentle about the process. There is no quiet vacuum chamber, no careful laser cooling, no patient researcher adjusting magnetic fields with a cup of coffee nearby. There is only gravity, enormous and relentless, pulling the remains of a star inward after its fuel has begun to fail. Under that pressure, matter is forced into conditions so extreme that atoms are no longer allowed to behave like the atoms we know from ordinary life. This is where degenerate matter enters the story. The name sounds a little insulting, as if the matter has made poor life choices and disappointed its relatives. But in physics, degenerate does not mean morally questionable. It refers to a special quantum condition where particles are packed so tightly that their behavior is controlled not mainly by heat, but by the rules of quantum mechanics. In ordinary matter, pressure often comes from temperature. Heat a gas, and its particles move faster, collide harder, and push outward more strongly. That is why steam can drive an engine and why a hot balloon can expand, but degenerate matter can resist compression even when it is not hot in the usual way. Its pressure comes from a deeper rule, a rule that says certain particles cannot all crowd into the same quantum state. That rule is connected to the Pauli exclusion principle. It applies to particles called fermions, including electrons, protons, and neutrons. The basic idea is simple enough to say gently. Certain identical particles refuse to be in exactly the same quantum condition at the same time. They cannot all pile into one state like sleepy bosons in a Bose-Einstein condensate. Fermions are more particular. They need their own quantum seats. If you try to squeeze many of them into a small space, they are forced into higher and higher states of motion. This creates a pressure that has nothing to do with ordinary heat. It is not the pressure of particles bouncing faster because they are hot. It is the pressure of quantum crowding. Imagine a theatre where every seat must be occupied by only one person of a certain kind. If the theatre is large, everyone spreads out comfortably. If the walls begin to move inward and the theatre shrinks, people cannot simply sit on top of one another. They must stand, climb, spread into higher rows, or press into any available space allowed by the rules. The crowd pushes back, not because it is warm, but because it cannot be arranged any more tightly without changing the conditions. That is not a perfect picture, but it gives the feeling. Degenerate matter is matter whose particles are packed into a quantum seating problem, and the seating rules are strict. In stars like our Sun, gravity is balanced for most of the star's life by pressure from nuclear fusion in the core. Fusion releases energy, and that energy helps support the star against collapse. The star is always caught in a grand balance. Gravity pulls inward, pressure pushes outward. For billions of years, this balance can remain steady enough that the star shines calmly from our point of view, although calmly is a generous word for a giant sphere of hot plasma constantly turning hydrogen into helium. Still, by stellar standards, it is stable. The star holds itself up because the energy from fusion keeps its inner pressure strong. But stars do not have endless fuel. Eventually the balance changes. A star like the Sun will one day exhaust the hydrogen in its core, expand into a red giant, shed its outer layers, and leave behind a dense hot core called a white dwarf. A white dwarf is one of the most important places where degenerate matter appears. It is roughly the mass of a star packed into a volume about the size of Earth. Try to pause with that for a moment. A star, something once vast enough to hold planets in orbit and shine across space, leaves behind a remnant no larger than a planet, yet still containing an enormous amount of mass. A spoonful of white dwarf material would weigh tons on Earth. It is not dense like iron. It is dense in a way ordinary materials never get the chance to be. Inside a white dwarf, atoms have been squeezed so tightly that many electrons are no longer bound to individual atoms in the familiar way. The matter becomes a sea of atomic nuclei and electrons, with the electrons packed into an extremely dense quantum state. The white dwarf does not keep itself from collapsing because fusion is still burning strongly. In most white dwarfs, fusion has stopped, or nearly stopped. It is supported mainly by electron degeneracy pressure. The electrons resist being squeezed into the same quantum states, and that resistance holds the star up against gravity. This is an astonishing thought. A dead star can remain stable not because it is alive with fusion, but because electrons obey a quantum rule. The star has run out of the ordinary engine that once made it shine, yet it does not collapse immediately into nothing. It becomes a kind of cosmic ember held up by the refusal of electrons to share the same state. If matter had no such quantum rule, the history of stars would be very different. White dwarfs might not exist as stable objects. The night sky and the evolution of galaxies would be changed by a rule so tiny and fundamental that it governs particles far beneath direct sight. White dwarfs are hot when they form, but they no longer generate energy in the way a normal star does. Over immense periods of time, they slowly cool. They radiate their remaining heat into space, growing dimmer and colder. Eventually, after times far longer than the current age of the universe, they are expected to become black dwarfs, cold dark remnants no longer shining. But the universe is not old enough for true black dwarfs to exist yet, at least as far as we know. Every white dwarf still has some warmth left from its past. It is like a cold from a fire that began in the deep history of a star, slowly fading in the long night of space. There is a limit, however, to how much mass electron degeneracy pressure can support. If a white dwarf becomes too massive, gravity overwhelms that pressure. This limit is known as the Chandrasekhar limit, named after Subramanian Chandrasekhar, who worked out the physics as a young man travelling by ship to England. The story itself is remarkable. A young physicist crossing the ocean, thinking about dying stars and quantum matter, realising that white dwarfs could not grow beyond a certain mass without collapsing. Science often has these quiet scenes hidden behind grand ideas. A person with a notebook, a journey, a question, and suddenly the fate of stars becomes clearer. If a white dwarf in a binary star system pulls material from a companion star and approaches this limit, the result can be catastrophic. It may explode as a type of supernova, a brilliant stellar detonation visible across enormous distances. These explosions are important to astronomy because they can be used to measure cosmic distances, and they are important to chemistry because they help spread heavy elements into space. The iron in blood, the calcium in bones, the metals in planets and tools, all are part of the long recycling of stellar matter. Degenerate matter is not just an exotic endpoint. It is part of the chain that helps seed the universe with the materials needed for worlds and life. For more massive stars, the ending is even more extreme. When a large star exhausts its fuel, its core can collapse violently. The outer layers may explode outward in a supernova, while the core is crushed inward. Under the immense pressure, electrons and protons can be forced together, forming neutrons. The result may be a neutron star. If a white dwarf is dense, a neutron star is almost beyond comparison. A mass greater than the Sun can be packed into a sphere only about the size of a city. The density is so extreme that ordinary atoms are gone. Matter has been crushed into a state dominated by neutrons, packed almost as closely as nuclear matter. A neutron star is supported mainly by neutron degeneracy pressure, along with other nuclear forces. Once again, particles resist being forced into the same quantum states, but now the particles are neutrons rather than electrons. The matter is so dense that a sugar cube-sized piece of it would weigh as much as a mountain, perhaps far more depending on the exact comparison. These analogies can feel exaggerated, but they are attempts to give human scale to something that resists human scale. Neutron star matter is not just heavy, It is matter pushed to the edge of what matter can be before gravity wins completely. The surface gravity of a neutron star is enormous. If you could stand there, which you absolutely could not, you would be flattened instantly. The magnetic fields can be incredibly strong. Some neutron stars spin rapidly, sending beams of radiation out into space. When those beams sweep past Earth, we see them as pulses, and the object is called a pulsar. Pulsars can be so regular that they act like cosmic clocks. A dying star's crushed core becomes a lighthouse in space, spinning and flashing with extraordinary precision. There is something beautifully strange in that. Matter collapses, atoms are destroyed, neutrons are packed into a city-sized sphere, and the result can be a clock more steady than almost anything humans once imagined. Neutron stars also remind us that the phrase state of matter can become difficult at extremes. What exactly is inside a neutron star? The outer layers may contain a crust of nuclei and electrons. Deeper down, the nuclei become increasingly neutron-rich. Further inward, neutrons may form a superfluid, and protons may become superconducting. At the core, scientists are not fully certain. The density may be so high that more exotic particles appear, or perhaps matter changes into forms involving quarks more directly. The inside of a neutron star is one of the great laboratories nature provides, but it is a laboratory we cannot visit, open, or sample. We study it by observing masses, radii, pulses, gravitational waves, X-rays, and the effects of neutron star collisions. The matter is hidden but not completely silent. In recent years, neutron star mergers have given scientists new ways to study dense matter. When two neutron stars spiral together and collide, they send ripples through space-time and release enormous energy. These events can produce heavy elements such as gold and platinum, scattering them into space. So the gold in a ring or a circuit may have part of its origin in the collision of dead stars. That is the kind of fact that sounds like it should be whispered slowly, because it turns ordinary objects into cosmic fossils. A shiny piece of metal on a finger may carry the history of neutron-rich matter, smashed together in a distant galaxy long before Earth existed. Degenerate matter is different from the states we met earlier because it is not mostly defined by familiar temperature-driven transitions. A solid melts because heat loosens its structure. A liquid becomes gas because particles gain enough energy to separate widely. A gas becomes plasma because energy strips electrons away. But degenerate matter appears when density becomes so extreme that quantum rules dominate the pressure. It can be hot or cold in different contexts, but its defining support does not depend on ordinary heat. In fact, degenerate pressure can remain even as the object cools. That is why a white dwarf can keep its size while it slowly loses thermal energy. The electrons are not pushing back because they are hot. They are pushing back because quantum mechanics gives them no room to all be the same. This difference matters. In an ordinary star, if the core loses heat, pressure drops and gravity can compress it. In degenerate matter, losing heat does not reduce pressure in the same simple way. The object behaves according to a different rulebook. This can lead to surprising consequences. For example, in some situations, adding mass to a white dwarf can make it smaller, because stronger gravity compresses the degenerate material further. That is not how ordinary objects behave. If you add more clay to a ball, the ball gets larger. Add more mass to a white dwarf, and it can shrink while becoming denser, until it approaches the limit where collapse or explosion becomes unavoidable. Matter under quantum pressure does not always follow household intuition. The path from white dwarf to neutron star to black hole is partly a path of gravity overcoming one kind of support after another. Electron degeneracy can support a white dwarf up to a point. Neutron degeneracy and nuclear forces can support a neutron star up to a point. If the remaining core is too massive, even these pressures fail. Collapse continues, and a black hole forms. At that stage, our usual discussion of states of matter becomes much more difficult, because the matter disappears behind an event horizon, at least from the outside. We can describe the black hole by mass, spin, and charge, but we cannot observe the internal state in any ordinary way. Gravity has taken the question beyond matter, as we know how to study it directly. This makes degenerate matter feel like the last visible defense before the darkness. White dwarfs and neutron stars are objects where quantum mechanics still holds gravity at bay. They are cosmic arguments between inward collapse and particle rules. Gravity says, "Come closer." Electrons or neutrons answer, "Only so far." That answer can hold for billions or even trillions of years in white dwarfs, and for long cosmic times in neutron stars. But if the mass is too great, gravity wins, and the story moves into black holes, where space-time itself becomes the main actor. There is also a quiet connection between degenerate matter and ordinary matter in your body. The electrons in atoms obey the same exclusion principle that supports white dwarfs. That rule helps explain why atoms have structure and why matter takes up space. When you press your hand against a table, the resistance you feel is not simply tiny hard balls touching. It comes from electromagnetic forces and quantum rules involving electrons that cannot all occupy the same states. The same deep principle that keeps you from falling through the floor also helps support a dead star. That is one of the great pleasures of physics. A rule can be present in the most ordinary touch and the most extreme stellar remnant. The table and the white dwarf are not similar in scale, but they are both shaped by quantum law. The word pressure can also become more mysterious here. We often imagine pressure as particles bouncing against walls. That works well for gases in a container. But degenerate pressure has a different flavour. It arises because confining particles to a smaller space forces their momentum and energy into certain allowed arrangements. Again, no equations are needed to feel the point. If particles are squeezed into less room, and if they cannot share all the same states, then the system pushes back. This pushback is not optional. It is built into the quantum structure of reality. A star can collapse until this pressure becomes strong enough to balance gravity, or, if the star is too massive, until even that pressure is not enough. This gives dying stars a strange dignity. They are not simply burning out, they are transforming into objects governed by some of the deepest rules in physics. A white dwarf is a cooled core held up by electron degeneracy. A neutron star is a crushed remnant held up by neutron degeneracy and nuclear forces. These are not ordinary solids, liquids, gases, or plasmas, though they may contain layers and regions with different behaviours. They are extreme states of matter, made not by a laboratory refrigerator or a spark of lightning, but by the weight of stars themselves. If you imagine the life of a star as a long breath, degenerate matter is what can remain after the breath is spent. The star gathers from a cloud, shines through fusion, swells, struggles, sheds, collapses, and leaves behind a dense remnant. That remnant may cool quietly as a white dwarf, pulse fiercely as a neutron star, or vanish behind the horizon of a black hole. In each case, matter has been taken far from the conditions of planets and kitchens. It has been squeezed until the old atomic architecture gives way. The particles that once formed atoms, molecules, dust, rock, ice, and living cells are driven into a deeper arrangement. And yet the story is not finished at neutron stars. If matter is heated not merely into plasma, but into temperatures like those of the earliest universe, or compressed and energized so violently that protons and neutrons themselves begin to lose their ordinary identities, another strange possibility appears. The particles inside protons and neutrons, called quarks, may no longer remain confined in the usual way. Matter may become a quark gluon plasma, a state not of atoms, not of ions, not even of intact protons and neutrons, but of the more fundamental ingredients moving in an extreme fleeting sea. After gravity has shown us matter crushed inside dying stars, heat and density will carry us further back, toward the kind of matter that may have filled the universe when it was still very young, and almost everything familiar had not yet taken shape. If degenerate matter shows us what happens when gravity squeezes the remains of stars into almost unimaginable density, quark-gluon plasma shows us what happens when matter is pushed in another direction, toward heat so extreme that even the particles inside atomic nuclei can no longer keep their familiar shapes. This is not the heat of a flame, or a furnace, or molten rock, or even the glowing plasma of the sun. This is heat from a much earlier and more violent part of cosmic history, the kind of heat that belonged to the universe when it was still young, dense, bright, and nothing like the calm, dark sky we see tonight. To understand quark-gluon plasma, we have to look beneath atoms, beneath electrons orbiting nuclei, beneath even protons and neutrons, down into the tiny ingredients that usually stay locked away inside nuclear matter. Ordinary matter begins, for most of our practical experience, with atoms. Atoms join into molecules. Molecules form liquids, gases, crystals, minerals, proteins, plastics, clouds, oceans, skin, wood, and tea. But atoms themselves have structure. At the centre is a nucleus, made of protons and neutrons, with electrons associated around it. For a long time, protons and neutrons were treated as basic building blocks. They were the heavy particles of the atomic nucleus, the dependable pieces from which elements were made. But physics kept looking deeper, and it found that protons and neutrons are not truly indivisible. They're made of smaller particles called quarks, held together by particles called gluons. The names sound almost playful, as if particle physics were invented by someone who had been awake too long and started labelling the universe with the contents of a dream. Quarks, gluons, strange, charm, colour, flavour. The language can feel whimsical, but the physics is serious. Quarks are fundamental particles, at least as far as current experiments can tell, and gluons are the carriers of the strong force that binds quarks together. The strong force is responsible for holding protons and neutrons together internally, and also for helping hold atomic nuclei together. Without it, the material world would not have the stable nuclear structures needed for chemistry, stars, planets, or the quiet existence of a pillow under your head. The strong force has a peculiar property. Quarks are normally confined. That means they do not appear alone under ordinary conditions. You cannot pluck a single quark out of a proton and place it on a tiny shelf, though one imagines the shelf would have to be extremely small and very well labelled. If you try to pull quarks apart, the energy involved does not simply let one quark wander free. Instead, new particles can form. The force between quarks behaves in a way that keeps them bound into composite particles like protons, neutrons, and other short-lived relatives. Quarks are like prisoners of the strong force, though the prison is also what allows ordinary matter to exist. But in the early universe, conditions were not ordinary. The universe was once so hot and dense that protons and neutrons could not yet exist as stable separate particles. The quarks and gluons were not confined in the usual way. They formed a hot, dense state called quark-gluon plasma. It was not plasma in the ordinary sense of electrons and ions like lightning or the sun. It was a deeper kind of plasma, a state where the ingredients of protons and neutrons moved in a shared sea, before the familiar particles of atomic nuclei had properly formed. If ordinary plasma is atoms opened up into nuclei and electrons, quark-gluon plasma is nuclear matter opened up into quarks and gluons. This is why the state matters so much. It is not merely another exotic entry in a growing list. It is a window into the infancy of the cosmos. In the first tiny fraction of cosmic history, the universe was not filled with atoms, because atoms could not survive. It was not filled with stable nuclei in the familiar sense. It was a hot, dense mixture of fundamental particles and radiation, changing rapidly as space expanded and cooled. Quark-gluon plasma belongs to that earliest material phase, before the ordinary matter of stars and planets condensed into the forms we know. To study it is to ask what matter was before matter became familiar. The idea that matter can change at this deep level follows the same broad theme we have seen again and again. Change the conditions, and matter reveals another possibility. Cool atoms enough, and they can enter a shared quantum state. Squeeze electrons enough, and they create degenerate pressure in a white dwarf. Heat a gas enough, and atoms ionize into plasma. Heat nuclear matter enough, or compress it enough under extreme conditions, and even protons and neutrons may dissolve into a quark-gluon state. Matter is not defined only by its ingredients. It is defined by what those ingredients are allowed to do under the conditions around them. But how can we study something that existed when the universe was incredibly young? We cannot travel back and scoop a sample from the early cosmos, which is probably for the best, because the early cosmos was not a comfortable place for sample jars. Instead, scientists recreate tiny droplets of quark-gluon plasma in particle accelerators. They take heavy atomic nuclei such as gold or lead, accelerate them to enormous speeds and smash them together. For a vanishingly brief moment, the collision creates temperatures and densities high enough for protons and neutrons to lose their usual identities. The quarks and gluons inside them become part of an extremely hot, tiny, short-lived droplet of matter. This droplet does not last. It expands and cools almost immediately, and quarks become confined again into ordinary particles that fly outward into detectors. Scientists do not observe the quark-gluon plasma by putting it in a bottle and watching it glow. They infer its presence from the patterns of particles that emerge after it cools. It is a bit like trying to understand the shape of a raindrop by studying the splash it leaves behind, except the raindrop is hotter than any star core we normally discuss, smaller than an atom, and gone almost before time has had a chance to clear its throat. Particle physics is not always designed with human intuition in mind. One of the great surprises was that quark-gluon plasma behaves less like a thin gas and more like an almost perfect liquid. Before experiments gave detailed results, many scientists expected it might act like a weakly interacting gas of quarks and gluons. But the matter created in heavy ion collisions seemed to flow collectively with extremely low viscosity. In other words, this most extreme state of nuclear matter behaved with a kind of fluid smoothness. It was not a random spray of independent particles. It moved as a strongly interacting liquid, expanding in patterns that carried the memory of its collective behaviour. That is a beautiful twist. At temperatures beyond ordinary comprehension, matter does not simply become chaos. It can become a nearly perfect fluid. The hottest matter ever created by humans revealed one of the smoothest flows known. The universe has a habit of balancing its strangeness that way. Go cold enough, and matter can become superfluid. Go hot enough, and quark-gluon plasma can flow with astonishingly low resistance. The mechanisms are different, the conditions are wildly different, and yet both challenge the everyday assumption that extreme states must be messy in the ordinary sense. Sometimes extremes reveal order of a deeper kind. The liquid-like behaviour of quark-gluon plasma tells scientists that quarks and gluons in this state still interact strongly. They are not freely wandering in the simple way the word plasma might suggest. They form a dense collective medium. When high-energy particles pass through it, they can lose energy, a process known as jet quenching. Again, we do not need the technical details to feel the meaning. The quark-gluon plasma is not empty space with particles loosely passing through. It is a real medium, so dense and strongly interacting that energetic particles are slowed and modified by their passage through it. It leaves fingerprints in the debris. The study of this state connects the smallest scales to the larger story. Quarks and gluons are tiny beyond everyday imagination, but their behaviour helped shape the entire visible universe. When the early universe cooled, quarks became confined into protons and neutrons. Later, protons and neutrons formed atomic nuclei. Much later, electrons joined nuclei to form atoms. Atoms gathered into gas clouds. Gravity pulled those clouds into stars and galaxies. Stars formed heavier elements. Planets formed from enriched material. Chemistry became possible. Life eventually appeared, and now, much later, a human mind can lie quietly in bed listening to a story about the matter that existed before atoms were born. That chain is long, but it is continuous. The matter in your body belongs to a universe that once passed through states, stranger than anything in ordinary life. There may also be quark matter inside the cores of some neutron stars, though this remains uncertain. In the previous part of the journey, we imagine matter crushed into neutron stars, where atoms disappear and neutrons dominate. But deep inside the most massive neutron stars, the density may become so high that neutrons themselves begin to overlap or break down into more fundamental quark matter. Some physicists have proposed hybrid stars, with outer layers of nuclear matter and inner cores containing quark matter. Others study whether entire compact stars made of strange quark matter could exist. These ideas are still being tested against observations. Nature has not yet handed us a clearly labelled sample, which is very typical of nature. The possibility is fascinating because it means quark-gluon physics may not belong only to the early universe, or particle accelerators. It may also exist inside some of the densest objects in the present cosmos. A neutron star could hide matter whose ingredients are no longer arranged as ordinary neutrons. If so, the boundary between nuclear matter and quark matter would not be only a moment in ancient history. It would be an active secret inside dead stars. Observations of neutron star masses, radii, cooling, vibrations and collisions may gradually reveal whether such exotic cores exist. The answer matters because it would tell us how the strong force behaves under pressures far beyond anything in ordinary nuclei. This is one reason scientists care so deeply about extreme states of matter. They are not just collecting curiosities, each state is a clue to the rules of nature. Plasma teaches us how charged matter behaves collectively, helping us understand stars and space weather. Bose-Einstein condensates reveal quantum coherence on larger scales. Superfluids show how friction can vanish. Degenerate matter shows how quantum pressure supports dying stars. Quark-gluon plasma reveals how the strong force behaves when the usual boundaries of protons and neutrons dissolve. Each state is a different experiment performed by nature, sometimes with help from human machines, on the question of what matter can become. The early universe changed state as it expanded and cooled. We often picture the beginning as an explosion, but it's better to imagine space itself expanding, carrying energy and matter with it, lowering the temperature over time. As it cooled, the contents of the universe passed through transitions. Quarks became confined into hadrons, the family of particles that includes protons and neutrons. Later, nuclei formed, later still, atoms formed. Each step made the universe more structured and more transparent. The cosmos did not begin with planets or stars waiting in miniature. It began as a hot evolving state where the rules allowed different forms of matter at different times. Structure emerged gradually as cooling opened new possibilities. There is something calming in that, even though the conditions themselves were violent. The universe did not need to decide all at once what it would become. It unfolded through changes of state. It cooled, it organized, it crossed thresholds. Particles formed, joined, separated, recombined. The familiar world is the result of a long sequence of material transformations. The fact that matter now sits quietly as stone, water, air, and living tissue is not a given. It is an outcome. It comes from the deep history of matter learning, under changing cosmic conditions, how to hold itself together. Quark-gluon plasma also reminds us that familiar particles are not eternal in their usual forms. A proton seems stable under ordinary conditions. It is part of the nucleus of hydrogen, carbon, oxygen, iron, and everything else that builds the visible world. But if conditions become extreme enough, the proton is no longer the right object to describe the matter. Its quarks and gluons become the better description. This is an important scientific habit. The best description depends on scale and condition. A glass of water can be described as a fluid. Look closer and it is molecules. Look closer still and it is atoms. Look into the nuclei and there are protons and neutrons. Look inside them, and there are quarks and gluons. No single description is wrong. Each belongs to a level of reality. That helps answer why states of matter are not just a simple count. At one level, water is solid, liquid, or gas depending on conditions. At another level, plasma is ionized matter. At another, quark-gluon plasma is deconfined nuclear matter. The categories depend on which ingredients matter most to the behaviour. In your glass, the arrangement of water molecules matters. In the sun, ionized particles and magnetic fields matter. In a heavy ion collision, quarks, gluons, and the strong force matter. A state of matter is not only a label for what something looks like, it is a label for the active rules controlling its behaviour. The creation of quark-gluon plasma in accelerators is also a reminder of how humans study the unreachably distant by building the extremely small. We cannot hold a star core or step into the early universe, but we can create tiny extreme conditions for incredibly brief moments, then surround those moments with detectors and patience. The machines are enormous because the particles are tiny. The detectors are complex because the event is fleeting. Thousands of scientists may work together to reconstruct what happened in a collision that lasted less than a blink, by so much that the word blink becomes almost useless. The scale of effort reflects the depth of the question. What was matter before atoms? What happens when the strong force is pushed beyond the ordinary confinement of quarks? There is also a lovely contrast between the violence of the collision and the subtlety of the information. Heavy nuclei smash together at almost the speed of light. The energy density becomes enormous. A droplet of quark-gluon plasma forms and disappears. Then, from the spray of particles, scientists extract patterns. Flow, suppression, correlations, ratios of particles, tiny clues. It is not unlike listening for a quiet melody after a thunderclap. The universe does not always reveal its secrets in neat displays. Sometimes it leaves a complicated aftermath, and understanding comes from learning which traces belong to which hidden process. In the story of states of matter, quark-gluon plasma is one of the deepest reminders that matter has a history. Solids, liquids, and gases feel timeless because they surround us. Plasma feels cosmic because stars shine now. Degenerate matter feels like the future of stars after their long lives. But quark-gluon plasma reaches toward the beginning. It asks us to imagine a time before atoms, before chemistry, before light could travel freely, before the first stars gathered from darkness. The universe was not empty. It was full, hot, dense, and rapidly changing. The familiar forms had not yet emerged. Matter was still in a more primitive state, not primitive as in simple, but primitive as in earlier, closer to the raw rules. This can make the room around you feel different again. The solid objects nearby are late arrivals in cosmic history. The water in a glass depends on atoms, molecules, electromagnetic forces, and temperatures gentle enough for liquid structure. The air in your lungs depends on atoms and molecules stable enough to drift together as gas. The calcium in bone, the carbon in cells, the oxygen in breath, all are forms of matter made possible after the universe cooled and stars created heavier elements. Yet the quarks inside the protons and neutrons of that matter are descendants, in a sense, of a time when quarks were not locked into the same familiar arrangements. Ordinary matter carries within it a memory of deeper states, though not memory in the human sense. It carries possibility. Under the right conditions, the layers can be undone, and so quark-gluon plasma sits near the edge of our map, but not at the end of wonder. It shows that even protons and neutrons are not the final word on matter. It links particle physics, cosmology, and astrophysics into one question. What forms can the ingredients of reality take when the universe is young, hot, dense, or violently compressed? The answer is still being refined. Experiments continue, models improve, observations of neutron stars add clues. The early universe remains partly hidden behind the limits of what light can show us directly, but the matter it once contained can be approached through theory and recreated in brief flashes on Earth. After travelling through the familiar states, the glowing plasma of stars, the cold unity of condensates, the frictionless strangeness of superfluids, the possible contradiction of supersolids, the crushed interiors of dying stars, and now the quark-gluon sea of the early universe, the old question returns with more weight than before. How many states of matter actually exist? It is no longer a schoolroom question with a clean little answer. It is a question about definitions, conditions, discoveries, and the many levels at which matter can organise itself. The list is not just longer than we first learned. It may never have had a single final number in the simple way we hoped. Matter keeps changing its behaviour when we change the rules around it, and as physics learns to create new conditions, the map continues to grow. So after all of this wandering through ice and steam, lightning and stars, ultra-cold atoms and crushed stellar cores, we return to the question that started the whole journey. How many states of matter actually exist? And the honest answer is wonderfully inconvenient. It depends on what you mean by state, which is not the kind of answer people usually want when they ask a simple question. But it is often the kind science gives when reality is refused to sit still for the photograph. If you ask in an ordinary classroom, the answer may be 3: solid, liquid, and gas. These are the states we meet first because they belong to the human scale. They're easy to point to. A rock is solid, water is liquid, air is gas. This answer is not childish or wrong, it is useful. It helps explain melting, freezing, boiling, condensation, weather, cooking, breathing, and why leaving ice cream on the counter is a decision with consequences. For everyday life, the familiar 3 carry a great deal of truth. They describe how matter behaves under the ordinary conditions of Earth, where temperatures and pressures are gentle enough for atoms and molecules to form the world we know. If you ask a slightly more advanced textbook, the answer may be 4: solid, liquid, gas, and plasma. Plasma is the glowing charged state found in stars, lightning, auroras, and certain human technologies. It is so common in the visible universe that calling it the 4th state almost feels unfair, as if the most widespread form of ordinary visible matter arrived late to the party and had to stand near the door. From the viewpoint of the cosmos, plasma is not an extra. It is central. Stars are plasma. The solar wind is plasma. Vast regions of space contain plasma. We on Earth live in a cooler corner where solids and liquids feel normal because our planet gives them room to exist. If you ask a physicist who studies matter under extreme or carefully controlled conditions, the answer grows longer. Bose-Einstein condensates appear near absolute zero when atoms enter the same quantum state and behave almost as one. Superfluids flow without ordinary viscosity. Supersolids combine structure and superfluid behaviour in ways that seem to contradict the old categories. Degenerate matter supports white dwarfs and neutron stars through quantum pressure. Quark-gluon plasma reveals a time before protons and neutrons were locked into their familiar identities. Then there are superconductors, liquid crystals, magnetic phases, topological phases, glassy states, supercritical fluids, and other specialized forms and phases that do not fit neatly into the old childhood list. At this point, the answer is no longer a tidy number. It becomes a landscape. Matter has many ways of organizing itself, and scientists classify those ways depending on which properties are most important. Does it hold a shape? Does it flow? Does it expand to fill a container? Is it ionized? Does it conduct electricity without resistance? Does it have long-range order? Does it break a symmetry? Does it behave collectively through quantum coherence? Is it held up by degeneracy pressure? Are its usual particles dissolved into deeper ingredients? Each question opens a different door. This is why counting states of matter is harder than counting planets, and even counting planets turned out to be more emotional than many people expected. Matter does not come with a simple label attached to each form. It does not say, "Hello, I'm state number 7. Please update your chart." Instead, matter behaves. Scientists observe that behavior, look for patterns, define categories, and revise those categories when new conditions reveal something unexpected. A state of matter is not just what something looks like to the eye. It is a pattern of physical organization. The old categories are based on visible behavior. Solids keep their shape. Liquids flow while keeping volume. Gases spread out. Plasmas are ionized and respond strongly to electromagnetic fields. But modern physics often classifies matter by deeper kinds of order. A crystal has a repeating arrangement. A magnet has aligned magnetic behavior. A superconductor has a collective electronic state that allows current to flow without electrical resistance. A superfluid has quantum order that allows frictionless flow. A topological material may have properties protected by mathematical features of its quantum state. These are not always obvious just by looking. A material may sit quietly on a laboratory bench, appearing perfectly ordinary, while inside it electrons are obeying rules that belong to an entirely different level of reality. This makes matter feel less like a set of boxes and more like a library. The first shelf has the familiar books: solid, liquid, gas. They are worn, useful, and easy to reach. The next shelf has plasma, bright and cosmic. Then come the colder volumes, the denser volumes, the stranger volumes with titles that sound as if nature was feeling experimental. Some books are thick and well studied. Others are still being written. Some describe states found naturally in the universe. Others describe states created only in laboratories under conditions so delicate that a little warmth or disturbance can erase them. Some may exist inside neutron stars, hidden beneath layers we cannot directly touch. Some may have existed only for a moment in the early universe, then vanished as the cosmos cooled. So how many states of matter actually exist? If we are strict and simple, we might say 4 major classical states for ordinary teaching. If we include well-established exotic states, the number becomes much larger. If we include all phases known in condensed matter physics and high-energy physics, the number is not fixed in any simple public way. There are dozens upon dozens of recognized phases and special states, and the list keeps growing as scientists discover new materials, tune interactions, cool atoms, apply pressure, use magnetic fields, and create conditions that matter has not often experienced on Earth. The more precise answer is that there is no final universal count that everyone uses in the same way. It depends on the context. That may sound unsatisfying at first. Humans like clean answers: 3 states, 4 states, 7 states. A number we can hold in the mind like a smooth stone. But the deeper answer is more beautiful. Matter is not limited to one short list. It is responsive. It changes its behavior according to the conditions around it. It can become rigid, flowing, gaseous, glowing, coherent, frictionless, superconducting, degenerate, deconfined, glassy, crystalline, magnetic, or something still waiting to be found. The number is not the real wonder. The real wonder is that the same universe can produce both a snowflake and a neutron star, both a drop of water and a quark gluon plasma, both a warm hand and a superfluid colder than almost anything in nature. Think about the ordinary glass of water again. At first, it seems like the simplest possible example of liquid matter, but inside that glass are molecules built from atoms, atoms built from nuclei and electrons, nuclei built from protons and neutrons built from quarks and gluons. Under one set of conditions, the water pours. Under another, it freezes into ice. Under another, it becomes vapor. Under extreme energy, the atoms could ionize into plasma. Under more extreme conditions, even the nuclei could be broken apart into deeper states. The identity of the material depends not only on what it is made of, but on the environment that tells its ingredients how to behave. A state of matter is therefore a relationship between ingredients and conditions. The ingredients matter, of course. Hydrogen is not iron. Water is not carbon dioxide. Helium is not silicon. But conditions are equally powerful. Temperature, pressure, density, magnetic fields, electric fields, quantum statistics, particle interactions, and even the shape of the system can decide what forms become possible. Matter is not a noun only, it is almost a verb. It is a way of being under the rules of a particular situation. This is why Earth gives us such a narrow view. Our planet is a calm middle place, not too hot, not too cold, not too compressed, not too empty. That middle place is perfect for life, but it hides much of matter's full range. In the kitchen, water behaves. In the stars, atoms are stripped. In the laboratory, atoms can become coherent waves. In white dwarfs, electrons hold up dead stars. In neutron stars, nuclear matter is squeezed toward unknown forms. In particle accelerators, nuclei collide and briefly recreate the kind of matter that belonged to the young universe. What we call normal matter is really matter under normal conditions for us. There is a gentle lesson here about perspective. A fish might think water is the natural background of existence. A bird might think air is the true open world. A star, if it could think, might consider plasma the ordinary condition of matter and find rocks rather quaint. We think solids are normal because our bodies are solid enough to touch them, our feet rest on them, and our homes are made from them. But the universe is larger than our habits. It contains conditions where our ordinary categories dissolve completely. Even within ordinary life, the borders are less clean than we first learned. Is glass a solid? Yes, in the practical sense, but its internal structure is disordered in a way unlike a crystal. Is jelly a liquid or solid? It holds shape but also wobbles, flows slowly, and depends on a network trapping liquid within it. Is sand a solid? Each grain is solid, but a pile of sand can pour like a fluid, jam like a solid, and form avalanches. Is foam a gas, a liquid, or a solid? It can be bubbles of gas separated by liquid films, or a solid structure full of gas pockets, depending on the foam. The world is full of mixtures, soft matter, granular matter, gels, emulsions, suspensions, and materials that behave differently depending on how they are touched, squeezed, shaken, or left alone. These examples do not always count as fundamental states in the same way plasma or Bose-Einstein condensates do, but they show why matter classification is subtle. Nature often gives us combinations and transitions rather than clean categories. A material can have one kind of order in one direction and another kind in another direction. It can respond like a solid over short times and like a liquid over long times. It can be rigid until stressed, then flow. It can be fluid until struck, then stiffen. Matter is practical, not polite. It does what the physical rules allow, regardless of whether our vocabulary is ready. That is where the idea of a phase becomes useful. In physics, a phase is a form of matter with distinct properties under particular conditions. Solids, liquids, and gases are phases, but so are many more specialized forms. A phase transition happens when matter changes from one form of organization to another. Sometimes the transition is obvious, like ice melting. Sometimes it is hidden, like a material becoming magnetic below a certain temperature, or a superconductor losing electrical resistance. Sometimes it is gradual, sometimes it happens suddenly. Sometimes it involves symmetry, order, energy, and microscopic structure in ways the eye cannot see. This means the question how many states of matter exist is a little like asking how many kinds of weather exist. You can say sunny, rainy, snowy, and cloudy, and for daily life that works. But meteorologists can speak of mist, fog, drizzle, hail, sleet, freezing rain, thunderstorms, cyclones, atmospheric rivers, heat domes, and many more patterns. The simple answer is useful. The deeper answer depends on how carefully you classify the sky. Matter is similar. The childhood list is useful. The scientific map is far richer. And the map is still changing. new materials continue to reveal new phases. Ultra-cold atom experiments create artificial quantum systems where interactions can be controlled with extraordinary precision. High-pressure laboratories squeeze materials into structures not found at ordinary conditions. Particle accelerators recreate tiny droplets of early universe matter. Observatories study neutron stars and their collisions to infer the behavior of matter at densities far beyond laboratories. Every method is a different way of asking matter the same question. What else can you become? Sometimes the answer has technological consequences. Understanding solids led to metals, ceramics, semiconductors, and modern electronics. Understanding liquids and gases gave us engines, chemistry, medicine, meteorology, and climate science. Understanding plasma supports lighting, welding, space physics, and fusion research. Superconductors are used in powerful magnets, medical imaging, particle accelerators, and sensitive detectors. Bose-Einstein condensates and atom interferometry may help with precision measurement. These strange states are not merely curiosities for late-night science narration, although they are excellent for that too. They often become tools once we understand them well enough. There is also a philosophical softness to the answer. Matter is not as solid a concept as the word matter makes it sound. At the deepest levels, what we call matter is excitation, field, interaction, energy, structure, and probability. The difference between one state and another is not always about different stuff, but about different organization. Ice and water are the same molecules arranged and moving differently. Plasma is atoms stripped into charged components. Degenerate matter is particles packed into quantum limits. Quark-gluon plasma is nuclear matter unbound into deeper constituents. The universe makes variety not only by having many ingredients, but by arranging the same ingredients under different rules. That may be the central answer to carry with us. Matter has no small final list because matter is not just stuff. Matter is behavior. A state of matter is a way that particles and fields cooperate under specific conditions. Some cooperation is familiar and stable. Some is rare and fragile. Some is cosmic and violent. Some is quiet and cold. Some last for billions of years in dead stars. Some last for a fraction of a second in a collider. But each one is real in the sense that it reveals a distinct way the universe can organize itself. So if someone asks you tomorrow, perhaps at breakfast, how many states of matter there are, you could answer kindly. You could say that for everyday purposes there are 3 familiar ones. If we include the stars, there is plasma as well. If we include modern physics, there are many more, and the exact number depends on how we define and classify them. That is not avoiding the question. That is respecting the universe enough not to pretend it is simpler than it is. And perhaps that is a good place to let the mind rest. The room around you is made mostly of ordinary matter in ordinary states. The bed is solid. The air is gas. Water nearby may be liquid, unless it is ice, steam, or patiently waiting to become tea. Above you, far beyond the ceiling and clouds, the sun shines as plasma. In laboratories, atoms are being cooled into shared quantum stillness. In old stars, matter is being squeezed into degenerate forms. In the memory of the early universe, quarks and gluons once flowed before atoms existed. All of these are part of the same story. The same physical universe, changing its expression as conditions change. Matter, then, is not a finished list. It is a vocabulary the universe is still speaking. We have learned some of its common words and some of its rare ones. Solid, liquid, gas, plasma, condensate, superfluid, supersolid, degenerate matter, quark-gluon plasma. Beyond them are phases with names that belong to specialized experiments, and perhaps others not yet discovered. The list expands because our reach expands. We cool more deeply, compress more strongly, observe more carefully, and ask better questions. So the answer is many. More than 3. More than 4. More than most of us were first told, but not many in a random way. Each state is a meaningful form of order, a particular agreement between particles, energy and the conditions surrounding them, and as you drift quietly at the edge of sleep, it is nice to remember that the ordinary world is only ordinary because it is familiar. The pillow beneath your head, the breath in your lungs, the warmth in your hands, the dark air in the room, all of it is matter behaving gently under the conditions that allow you to be here. Beyond that gentleness, the same matter can glow like a star, flow without friction, hold up a dead sun, or return in thought to the first hot moments of the cosmos. If this quiet journey through the many moods of matter brought you a little calm, a little wonder, or simply a softer place to rest your thoughts, I would be grateful if you liked the video and subscribed. It helps this peaceful corner of physics find others who may enjoy drifting through the universe one gentle question at a time. For now, let the question loosen. How many states of matter exist? Enough to remind us that reality is wider than our first lessons, softer at the edges than our categories, and always ready to become something new when the conditions are right. Sleep well, fellow traveller, wherever you are surrounded by matter in its familiar forms, while the stranger forms wait quietly in stars, laboratories, and the deep memory of the universe.